I'm going to do the first 1.5 hours with a camera, and then after that I'm gonna remove the camera. It's a lot easier to stream without the camera, and a lot easier to think as well. So, because I'm thinking about staying more time today, I want to do it like that. And I'm going to continue to work on the poker tool. I think I'm gonna start with doing the Italian stuff. And I solved the issue yesterday. I figured out how to make this work, and the problem wasn't with the security settings, was just the file, because I was accessing the folder and not the files themselves, and you have to get the file directly, which makes a lot of sense. But today what I'm probably going to do is to create a script. I'm gonna make the file now. It's gonna be analysis, I think. And I'm gonna try to see different ways that I can use this data here from this file to structure the information, and I'm going to study the UPI to see how I can use different ways that I can connect to Power Solver, and different things that I can do with the UPI that they provide. And I'm probably going to use ChatGPT to help as well. So that's the goal, I think.
Fa,
Fa,
Does.
fisso,
fisso,
Set. Unchanging.
3,
3,
3.
desiderare,
desiderare,
Desire.
aria,
aria,
Air.
bene,
bene,
Well.
anche,
anche,
Also.
giocare,
giocare,
Play.
piccolo,
piccolo,
Small.
fine,
fine,
End.
mettere,
mettere,
Put.
casa,
casa,
Home.
leggere,
leggere,
Read.
mano,
mano,
Hand.
portare,
portare,
Carry.
grande,
grande,
Large.
compitare,
compitare,
Spell. Words.
aggiungere,
aggiungere,
Add.
anche,
anche,
Even. Also.
terra,
terra,
Land.
qui,
qui,
Here.
devo,
devo,
I must.
grande,
grande,
Big.
alto,
alto,
High. Tall.
tale,
tale,
Such.
seguire,
seguire,
Follow.
atto,
atto,
Enact.
perché,
perché,
Why.
chiedere,
chiedere,
Ask.
maschi,
maschi,
Men.
cambiamento,
cambiamento,
A change.
è andato,
è andato,
He. She went.
luce,
luce,
Light.
tipo,
tipo,
Kind of thing.
spento,
spento,
Turned off.
bisogno,
bisogno,
Need.
casa,
casa,
House.
immagine,
immagine,
Image.
provare,
provare,
Try.
noi,
noi,
Us.
di nuovo,
di nuovo,
Again.
animale,
animale,
Animal.
punto,
punto,
Point.
madre,
madre,
Mother.
mondo,
mondo,
World.
vicino,
vicino,
Near.
costruire,
costruire,
Build.
se stesso,
se stesso,
Himself.
terra,
terra,
Earth.
padre,
padre,
father,
So you see here that I get these outputs. But I think I'm gonna have to study the UPI anyway, because I'm not really sure like what are the other order to do things. And how I should put the information here. Because here it seems like it is separate the way that you have to put the combinations in one line, and then or maybe it's just one command and then there's one output there. Let's see, range. Yeah, I think this command shows the hand, and then this command shows the range. So you have to put the range separately. That's the thing that I don't understand. But this example is just to see like a file. That's the thing. Yeah. It's showing the metadata for the file path and loading the tree. So I'm gonna have to study the UPI for the stuff that I wanna do. And here, the thing that I have to do today is to figure out how to get the positions based on this stuff. Based on the actions and the rounds. But now that I realize that, yeah, I should change this script actually, the parse data, because the way that it is here is gonna be more difficult because it's separated by players, by actions, and not by players. So it becomes more difficult to know or to think about how to translate the sequence of actions into the positions. I think I'm gonna take another picture as well, because this one doesn't contain a lot of information. So the way that I was gonna do it is to get the number of players in the beginning. Yeah, so I can create a count variable. I'll put here. Actually, here. And then each time there is a player seats, and that's the thing I have to see. I think it's only gonna happen in the beginning of the hand. And I think that the other places it doesn't happen. So it's only gonna happen. This pattern is only gonna happen here. So each time that this happens, I increase the player count. And then I use this player count on the rounds. Thing is, I don't remember really well, because the problem is because here is only showing 3 actions, but let's say that the first and the second is gonna be small blind and big blind, but let's say this one is on the cutoff instead of in the early position. But since it's the only person that played, then it shows right after the other ones. And then if I just do by subtracting, then it's gonna get it's gonna say that this is early position, but it is cut off. That's the problem. So let me see if I think I deleted the other, so I'm gonna create a simple script again to just get the hands. Just copy from this. Also think I'm gonna delete this data show here. And I'm gonna refactor this, should be data 1 or data. It's weird because the last time I think I only see 2 players on the round number 0. So it's weird that in this picture the fuck? It's showing 3 actions here. Oh, here. How can I do this? The thing is that most hands probably only 2 people play pre-flop, so that's why there isn't a lot of. But then I think it makes it impossible to be 100% accurate. Or I guess I can just ignore the other actions as well. So I think that's what I'm gonna do. Because if I count, then it's impossible. But if I don't count them, then I can just assume that the player that is gonna be the first tracked on the round number 1 is gonna be the one is gonna be early position. Or it's gonna be small blind, actually. Or maybe this happens when you have like a new player, because usually when you get into a table, you have the option to post the blind and start playing right away, or to wait for the big blind. So I think that this situation only happens where you have 3 actions here when someone enters the table. So this third person would be someone that's posting the blind, and the other 2 would be small blind and big blind. Now the other thing that I want to make sure here, here is different as well. That's the thing. So the round 0, the player 1 is small blind, but then here the action is hero 3. But I'm pretty sure small blind plays first. And then, yeah. The first tract is small blind, and then after the post blind. So, oh, round number 1 is pre-flop. That's the thing. So this is just posting the blinds. Round number 1 is pre-flop. And then pre-flop is early position, the first, I think. I don't even remember anymore. I don't think about it anymore when I play, so... But it's early position, I think. The first one tracked pre-flop. Or is big blind. No, it's early position. That should be early position. Because otherwise it wouldn't make any sense here. Because this is small blind and this is big blind. And hero is neither of them, so it's early position first, I think. And then the last is big blind, yeah. So what I'm gonna do is get on the round 1, on round 2, get the small blind, big blind. So round 0. My problem is that the way that I'm doing this thing here. I could just add. I can do the same thing that is doing here, but I can just access these current players. If currents. Oh, it is gonna be the round 0. Yeah. And that's the thing, is only gonna access these ones. So I can't do it here. So it has to be on the action. Actually, I don't need to use round 0, I think. I can just get everything from round 1. It's easier that way. Then I start at the early position and then I just subtract based on the number of players. Or maybe it's gonna show all of the actions anyway. I think I'm overcomplicating this. It's gonna show all the actions on round number 1, and I think it's always gonna be... the situation where it changes is when you have less players on the table. That's why you have to subtract. There's 1, 2, 3, 4, 5, 6, 7. Alright, position, cut off. Bottom, small blind, big blind. Oh, it's because that's also a situation where it changes when you have a 3-bet, I think. I did small blind 3-betted here. Then the big blind folded and I called. So you can't rely 100% on the number of actions, but you can rely that if I subtract, then it's gonna be the last one is gonna be the big blind tracked. I get the number of players and then I decrease each time I add a player. I decrease the thing and I make the position. But I have just to see at what point I'm gonna add here. I have to see the order, I think. So I'm gonna assume that I'm doing this on round 1. So right after the players and the rounds, it's gonna be on actions. And that's the problem. So here's where I'm getting the actions. But this is based on the other stuff. This is separate, I think. I'm confusing the two. So if current round is not, so it's here that I have to do it. Because here is gonna determine the current round, and then here it creates the action. So it's very confusing, but I think that I put here and then I put position here instead of type. That's what I was gonna do. And the thing is, because it's not supposed to be on the... Yeah, what I have to do instead is create a condition based on which round it is. And I have to change another parts. I'm gonna do something with player count, but I'm not gonna change the action. Yeah, but the problem is that it's gonna give me this warning because it's gonna say that it might not be initialized at this point. So what I can do is initialize to 0 in the beginning. But then each time I can do, but then initializing both like two times doesn't seem like the right thing to do. But I think it solves the warning there. And it is like, it's a warning that makes sense, but I think it's safe to do the thing that I'm doing because I know that each time is gonna have this line, so and if it doesn't, then there's something wrong with the hand. But it is like, because there might be a situation where it doesn't, then the program is gonna run, but then it's gonna have, I'm gonna have a bunch of mistakes because the player count is gonna be wrong. So I remember I got a warning similar to this when I was building this thing with Rust, and then I realized that actually it's correct to give the warning. It's a light warning, so it means that it's gonna run anyway, but so it's probably not the best to do it like this. But what I'm thinking about is like each iteration is gonna start the hand because it reads line by line. So when it starts the hand, it's gonna be when it catches this line, which is on the beginning here, and then it's gonna create the current hand object, and then everything on the hand after that is gonna be based on this object here. And here I'm creating the player count because I wanna increase in this position here, because then I'm gonna get how many players there are in the hand. And then I'm gonna use this number in this round here to see the position of the players. If it is round number 1, it means that it is pre-flop, and then I put the first player. That's what I have to think. No, this because I think I'm not gonna have access to the action. That's the problem. I do have access to the number here, right? Yeah, so what I'm gonna do is I'm gonna put round number, then I'm gonna make it equal to this. And now that I'm thinking about it, I can just use current round. Don't need to do this again. But then it might be one of those things where it's gonna give me this warning again because it might not exist. But I'm gonna test it like this. Just remove this. Well, actually no, it's different. Because yeah, I'm messing up. Because this one is for the line right now, which is the line of the action, so it's the number of the action, not the number of the round. So it's actually action number. That's why I did it like that. So even though the code is the same, the line is different, so it changes the number. So here, then I put action number here. And then based on the action number, I increase the player count. But I think I'm just gonna put here. Actually, I should copy. Because I need it twice, because I need to renew the player count each hand as well. Yeah, but it seems like this is the way ChatGPT did it, so I think it's fine to do it like this. It's not giving me a warning, I think, on the other ones because it initializes here. So even though you have this, you potentially have the same problem where if there is a mistake because the line for some reason doesn't show up in the hand, then it's gonna give me wrong results, even though it's gonna run, because it's not gonna reset the loop. But the problem is you can't put on a try catch block because, or try accept block, because it's gonna run one line at a time. So obviously most of the lines are not gonna have this pattern. So yeah, but I still think it's giving me the warning there. So it's probably because it's giving the warning for the other stuff that ChatGPT did as well. It's probably not the best, but probably works. No, I know it works, but it's not the best. I think I'm gonna leave it like this. The other thing that I don't know, and because I don't know if there is worth spending a lot of time now, is because I'm not sure if the hand formatting is always the same. I don't remember. I think I got this hands from Holder Manager, but I'm not really sure because there might be different formats for hands. Then I'm gonna have to change this anyway to parse the different format. But I think this is fine because I know that there's a very high probability that like it's gonna be on the correct format, because otherwise it wouldn't work on the Holder Manager software. Yeah, so if it's the first round, let me think. So the first position is gonna be early position. I need another flag variable, I think. Yeah, because I need to decrease from the flag variable. Oh, actual number. So if player counts equal to 0, not equal, it should be greater. And the problem is not gonna run then on the first iteration. That should be greater or equal. I remember I did some kind of calculation as well, that I made a mistake in the beginning. And pretty much what I'm trying to think about is then how I'm gonna put the position. And it's also a problem because I'm gonna have to put the position here on the action object, but then on the round 0 I'm gonna have to put the position as well. And the issue is the structure of this, because it's based on the action first, and then each player has, like, the action is a dictionary with the rounds, and then each round has a player, I think. As players, then, so each player is an object, the object has actions. Yeah, so it's separated by players, and then, so I'm probably on the wrong. Yeah, but that's the issue, that's what makes it difficult. Because it would be better if I put it here, obviously, but then because of the sequence of lines, I can't do this, because when I'm defining these things about the player, there is still no rounds. Oh, so what I can do is just change, obviously. Yeah, but it still needs... Yeah, so I don't need to change the action. Yeah, that's what I was gonna do. So I'm just going to modify the player's object. This... The problem is, how do I get the player names? The thing is that I don't want to change everything again, because then I'm gonna have to think about all the other stuff. Because I think that's obviously, based on what I'm trying to do, it would be better to do it on another structure. Is that way how I'm gonna keep track of. I can think about the order that they're being inserted, but it doesn't seem that good. And here it seems redundant as well, because I'm getting the name of the actions and putting the name again. Let me think. Because this is more getting each player than all of the actions for each player. It seems like inefficient. It would be better to get the positions first of each player, and then only get the players that played the hand on this players array here. Name, chips, pocket cards. Another thing is I wonder if they... The thing is I can't assume that they are... They're probably not on the correct position on this player's thing here. Or maybe they are, because here is hero, hero, P3, P2, and P5, CP3. I need to run the other one again. Let's see. So maybe they are in order here. That makes things a lot easier. Yeah, I think they are on the correct order here. So I'm overcomplicating things. So yeah, the only question then is, if there are less than 6 players, is it gonna be like what happens? Because now obviously they don't have 6 positions. But I think here they are in order, because here's player 1, then player 1, then player 2, player 3, player 4, hero, and player 6. And then the other actions are just... Oh no, this is the tie. Player 1, player 2, player 3. Yeah, so I think it is on the correct order here. So I don't need to do this stuff. The only question is if there are less than 5. So I think I can figure out pretty easily by changing this script based on the player count here that I did. But I'm gonna change this stuff that I did on the round here. And I'm just gonna get it based on that. That makes things a lot easier. I'm gonna put a comment here as well to remember. So I actually can do it. Yeah, this way it becomes a lot easier because I can do it here. But I need a variable anyway to... So this player count, and then I just put it at the end here to know which order it is here. Then I can create a map, I think, to keep track of the positions. I can just use the number. I'll be right back. Alright, I'm back. Yeah, so I think I need the variable anyway because I need to keep track of the sequence of players. And I think I can create a dictionary to keep track of the position. So the first one is early position, I think, and then it goes until the big blind. Yeah, so I think I have to create a script first to see the number, to see what's gonna happen if there isn't 6 players. Three, 4, 5, 6. And the first one is early position, the last one is big blind. On this order here. So I'm just gonna write this here and then I'm gonna change the other script to figure out what's gonna happen when there are less than 6 players. I have a count here. And the thing is, so I need the other elif statement. Elif player 6. Let me think. Because I want only to start printing the lines after the player count is less than 6, but if I put it here a condition, then it's gonna print the lines before anyway. So I need another flag variable, I think. Yeah, I can just put another elif statement here. I don't need this stuff here. I think this is gonna work. Oh, that's the problem because it doesn't exist here, so yeah. Let's put here. Put it in here. So let's see. So it looks like this one is bugged. There are no players here. I think maybe I should do this on the other script as well. Like I should encapsulate everything else based on this line here, I think. Because then I have a block. So I'm gonna know that it went through, and then that solves the other issues. And then if there are no players here, then I just skip the hand. So I do the same thing that I did here with the flag variable, and then I put all the other conditions of this script inside of the main condition, which is to check to see if the flag variable is true. Put here, here. Then I'm gonna make one based on this condition here. And then I put all the other ones. Except this one. Inside of that. Is that way it then is only gonna get information if for the hands if there are all players. If it is not bugged like that. Hopefully this doesn't break the other stuff. But maybe it's the way that I did this thing here, because now... But I think this is better anyway. It's more robust. But I think it's just the way that I did the script, not that there isn't any players. It's because I'm only printing the lines when seems true. So I probably shouldn't put this variable here to just print everything. But I think I'm gonna leave it like that on the other one. One, two, three, four, five. So I think there's something wrong here again. Because the way that I is printing. And because it's not gonna print the other lines, that's the problem. Let me think. Because I need to print all the lines until it gets to the point of the rounds. I want only to print the hands when there are less than 6 players. And the issue is I can only get the count after it reads these lines here. So obviously I think I should do the other way again. And then just print the line here. And then print the line here as well. See, this works. Because the issue is then it's not gonna print the other lines for the rounds. Oh, and's always false here. Didn't make. I think if it does make sense to put the other line there, make and equals true, if it's gonna change anything. I think it doesn't. I have another idea. I'm just gonna put. I'm gonna do more simple way. I'm gonna put it on another list outside, and then I print the list at the end. And now I'm thinking about it if it makes sense, but I think it's not gonna change anything. And I think it probably is better to do it like this, because then like I make sure that I captured all the players in the hand, and then only if I capture the players on the hand, then I capture the information. Yeah, but the problem is because then I'm messing it up here, so it doesn't make sense actually. Yeah, so I'm just gonna erase this thing. Actually, let me do the other way around to see. Make sure that I got the indentation correct. But I think it would be better though if I did it. But then it's gonna get too complicated, because then I'm gonna have to put all this stuff here on all of them. Maybe I can just add here and all players, but I think it doesn't matter that much, so I'm just gonna leave it the way that it was before. So here I think I'm gonna make the condition based on the end of the hand. So let me see where this... I'm just gonna copy this one and then remove the stuff that I don't need. It's easier. The way that I'm thinking about it now is appending the information for the hand on the list at the top and then printing the list instead of making based on the... and then I make a condition based on the amount of players to only append the lines that contain last, but then I think that it doesn't... it's still complicated. There's probably a better way, an easier way to print only the lines. Because they should want to print the lines up to the round 0 or the round 1. I want to print the players and the round 1 because that way I'm able to make sure that, or to see what's going to happen when there is less than 6 players. Like how the positions are going to be structured. Because obviously it's not going to be... like some positions are gonna be lost, but you still have the big blind, so it still goes from early position to the big blind, but then the positions in the middle are lost, and I want to know like how I'm gonna structure that. Because obviously the easy way would be to just... and I think that's what I'm gonna do, because like, even if I get the information, then it doesn't matter because it's not gonna show me anything about the position of the player. It's just gonna show the sequence. So there's no way for me to know exactly what position. But then I could just based on common sense, that I assume that I'm gonna assume that the early position and middle position don't exist. I'm gonna go like that. But the problem is that I start counting from the first position. That's the issue. Because when it reaches this line here, like I don't have any players yet. So the issue is I would need to have the player count here to know the total amount of players in order to be able to put the position of each one. So in this case, like if there's only 5 players, then the big blind's missing, then if I do it like this, then it's gonna assume that it's gonna get all the positions up to the big blind, but then it's not gonna have the big blind, the hand's not gonna have the big blind. And what I wanted to do is to do the other way around, where it subtracts for the first positions that it has. So instead of not having the big blind, you wouldn't have the early position. But because of the sequence here of lines, I can't do it like that because I'm starting to count from this point. Then the question is how I'm going to know how many players. I guess I can update later. I think what I have to do is use a dictionary and then I put the information of the player name and the position. Yeah, what I'm thinking about now is doing a dictionary where I put the, or two dictionaries. One I put the name of the player and the player counts, and the other one I put the positions. But I guess I can just use the dictionary as well to, and then make if-else statements. Like, because then when it hits this line, the slash players, I'm gonna know. So when he reaches this line here, then I can make a condition here, elif, and this line. And then when he reaches here, I'm gonna have the player count already based on this. And then if I cache the name of the players with the order of the counts, then I can make the calculation. And that's probably what I'm gonna do. And then I think that's what I ended up doing on when I did it with Rust. And a lot of reflection on it. You can see the mouse. Put some other music. Yeah, so what I'm thinking about now is to do like this. The question is, what is the easiest way? If I should create two dictionaries, because I kind of don't want to do that, because then it's more stuff to put here on the beginning. So I think one extra dictionary is inevitable, because otherwise there is no way to keep track there. So I initialize here, then to keep track of the names and the sequence of the player counts. And then when it reaches this position, then I do this stuff here. Where I access the dictionary and see the... yeah. So if I do... Now let me think about a name. Player map, or... a player map, maybe? And I have to initialize this here, probably. There's here. Yeah, this is the thing. Player name, probably. Yeah, now I have to do the calculations actually. The player counts equals... oh, I already did player counts. So player total equals 6 minus player counts. Or player spread, maybe? Is it? In this, I remember I did it wrong in the... when I did it with Rust, because it's kind of confusing, the calculation. But pretty much what I want to do is check to see if there is less... I'm probably gonna put a condition here, actually. Just check, yeah, I can make the condition to see if this is 0 or lower than 0. Player spreads. lower than 0, then I do something, and if it is not, then I do something else. Because if this is lower than 0, then it means that, or actually it's the other way around. It's greater than 0. It means that there are less than 6 players. And then I have to do a calculation to just see how many players there are less. But this is gonna be the player spread actually. It's very confusing. What I wanna do is get the spread and then I just advance the positions, let's say. Like change the if-else statements to get the position of the players. And I have to do this actually. I think. A current players then not name. Oh, actually, it's the other way. It's inside of the condition here. Oh, but this doesn't work also. Yeah, what am I talking about? Actually, it's confusing because I didn't do the map here. But I'm gonna use the other map, I forgot. And then on this player map, I'm gonna start the positions based on the player count here. So. And that's what I want to do. So if the name is not on the map, then it adds with the count. So now I have to think about this. Kind of annoying because it's not hard, but it's confusing. So it's annoying to think about. So when it gets here, I'm gonna have the total amount of players. So if it's less than 6, then player spread is gonna give me the amount. So that's the thing I have to think now, because in Rust I use match, but ideally I wanna be able to add the spread to the number, I think, or player count plus. Because the way that I'm doing here, maybe it's better to do the other way around, where the key is the player count. Yeah, I think I need the other dictionary to keep track of the positions. That's probably better, instead of doing if-else statements here. Because if I do if-else... And I'm gonna have to access this this object here with the name to add the information later. Let's see, if I do if-else statements, how am I going to do it? I can't really do. So this checks to see if it's 0. What I can do is change the values here based on the player spread. That's what I can do. Then I can do if statements. Well, I think it makes sense what I'm doing. Actually, it's not gonna be like this. It's gonna be a loop because I have to loop over the players. This is only one line, so. Actually, it's much better if I do it like this. I'm trying to think about the name. I'm gonna loop over the items of the dictionary. That way I access the key and the name of the player. Maybe position, maybe. If position equals 0, blah blah. Yeah, that's what I'm gonna do. So increase the. I'm gonna do this loop again here for our players. I think I need to access the position. Okay. And the problem is if I increase each one by this spread, it doesn't work. Because then the last positions are gonna be over. There's two different ways that I'm thinking about, and it's kind of confusing. One is using a dictionary for the positions, and then I update the values of the values of the value of the player map for each player to get the correct value for each one. If it is less than 6, and then I use that to get on the map their position. That's one way, and the other way is to make a bunch of if-else statements here based on the position, and then just update the values for each player on the player map based on the player spread, which is the updated amount of how many players that there are, I think. And so this is the value that I have to change it to do. But then I can't use that to check then. Maybe I do player spread and then I do total players here. It's player spreads minus player counts. Or player count minus player spread. But the issue with this is that I still... let me think. Because the way that I'm gonna get in the beginning is from 0 to the whatever the position is. And maybe it's 5 instead of 6 because I'm starting from 0. And 0, 0, 1, 2, 5. So it's 5, I think. So usually the 0 would be early position. Maybe it's better to do the other way around, where, because I think it's more intuitive this way. So it's initialized as 1 instead of 0. The first position is early position. So if there's 6, but if there's 5, then it's gonna subtract from this, let's say. So it's gonna be 1 to 4. Yeah, so the way that I update it, I just make it base, or I don't even need to do total players here. In this case, it would be true, so if I increase the values of each one by 2, it would go up to the big blind, I think. Or the position would be this, and this, cut off this. I'm just trying to think if this way, like there's some edge case that is gonna be, because I think that's, I have to be careful, because last time I remember that I was on like this exact part that I did something like this, and then like I got an error that I had to spend, and the problem is that I think it was something that I realized that it was wrong only because of something else. So the issue here is that it might run and be everything, like everything could work, but then it's still wrong at the end. So that's why I'm spending time thinking about it. But I think I can just increase the value based on the spread for each player. So do pretty much position as equals player spread. And then I don't even need this. And then here I just put a bunch of if-else statements to check, and then I use this thing here. I think I need to do another if statement here. So if this name is equal to player, then that's the problem, because this is gonna be an array. That's the issue. So I need to update this dictionary here, but this is an array inside of the players. It's this thing here. I obviously can just loop, but then I'm thinking about it, because then I have to do the same loop a bunch of times. I obviously can do another for loop there as well, outside, and then it's gonna be a nested for loop, but So obviously what I'm gonna do here is put the position for each one up to 6, or this starts with 1 as well. So from 1 up to 6, and then for each one I put the position that it would be. So this works like kind of like the mapping or the match in Rust. But then the issue is that this is an array. So the thing that I'm thinking about is obviously that I have to change this data structure, but then the problem is that it's gonna change everything else. And this I'm trying to think like if there is a way to change this that is not gonna change all of the other stuff. So obviously the first thing that is coming to my mind is to do an object here instead of doing a list for the players. I do an object. And then the issue with that's let me think. Because obviously you can't put all the players on the same object, because then the keys have to be different. So if I do it like that, then I have to change all the keys and it changes everything. So another alternative is to create the object outside and then just put one piece of information on the object outside that is going to be unique to each player. I guess I can do it like that with the position, but then the problem is that I only get the position after. Like, you would have to get all of the... The other alternative is to put this list outside and then just... But then it's the same thing. Like, if I put the list outside and then I use the list to create the object, and then I use the object to put here, then it's the same thing as looping through this list on this part here, or this part. I guess the easiest thing to do is to just figure out what is the best way to get all the players from here, which is obviously using a loop. But then like putting the loop because the issue is I don't know if I can change the object that way. Oh, let me see on the action part. Yeah, so it did it like this. And so I guess I'm gonna do it like this. Just loop outside and then I just put another information. And we're gonna copy this stuff. The thing is that I'm not sure, and the reason why I'm spending time thinking is because there might be a... Like, that's the most difficult part, is thinking about a way for structuring the whole thing. And the reason why it's challenging is because I'm looking at stuff line by line. So obviously if I could look at the whole thing at once, then it would be a lot easier to come up with a data structure, I think. That is gonna be the best one possible at the end to analyze things. And because I extract information line by line and the order can be confusing, then exactly how to put each thing becomes a problem. Becomes very difficult. Yeah, but so what I'm gonna do here, like I have to do it outside of this thing. I'm also trying to think about a way that to avoid using an nested for loop here, so it is faster. But I'm not sure if I can do that. Because I have to access all the players. Maybe I can use an object outside. And then I loop and I map. that way, yeah, that way is faster, I think. So I do the same stuff there. So what I'm thinking about is creating an object here, and then I put the names on the object. Or I can create a set and then just put the names on the set. And then I use the set to... Oh no, because I need to add the information anyway. Because I'm gonna do player, then position. And it's gonna be equal to position. That's the thing. Or actually not, it's gonna be based on the condition here. It would be like big blind. Or small blind. And so on. Based on this condition. That's why I think I can't avoid the nested for loop. But I think I can because the names are the same, so I can just use the player map here. Yeah, that's what I can do. Alright, player. Player naming player map, then I use that. Yeah, that's how I do it. Then I put player. Why am I getting this mistake here? Oh, it's equal, not... Yeah. So I think this way it works. Obviously getting these mistakes here. But I think that is just something from PyCharm because it's saying that it's expecting a number. I don't understand why it gives me this mistake though. This string is supposed to work. Current round players. And players. So I'm looping through the players and then I'm getting their name, checking to see if they are on the map. If they are, I get the value for them of the position. And then I change here based on the spread if there is less than 6 players. And then I can make the conditions here, which are gonna be the same. Just gonna change the value there. And this thing. I think this should work. I wanna see why I'm getting this thing here, expected type things. I'm gonna search for this. Alright, sure. Interesting. There we go. I don't know why it does that. I don't think that's an error. I can't see why this would be a mistake. I'm trying to think if it's something about the code that might be wrong, but like the key is gonna be the string, so I think it's just something from the interpreter, from PyCharm. And these mistakes are probably because of the order of things that it might not have. This is also I don't understand. Yeah, does not define set item. So it's thinking that it is a string, but it isn't. Like it's the object value. So it's probably something from the interpreter that, because this is an object, you're supposed to have this set item property if you want to make it equal to the list. Yeah, I don't understand really well. Yeah, unresolved attribute reference for append for a class string. So it doesn't understand that it is an object. So I think that's fine. Whatever. Maybe. Yeah, so I think this should work. So I'm mapping through I'm going over the players array, and then I'm getting the numbers, seeing if they are on the player map. And then based on their name on the player map, there's going to be the value of position, and then based on that I add the position to the player dictionary. Yeah. So I think I'm going to put data true here, just so, yeah, so I don't screw up this one. I'm going to run this, and so. Can only concatenate string, not int to string. So the problem is here. But it, this position should be the value of player count here. Player name not in player map. Player map. Player counts. I think like the easiest thing to do is just print. Why is not? Oh. So 0 and 1. Oh, so it's the other way around. Oh. Oh yeah, because the key is the value of the key is the name of the player, right? Confused myself there. So now it should work, I think. I'm gonna get something to eat, and I think I'm gonna read the Ethereum book. While I eat, I'm gonna remove the camera, and then after that, I'm gonna check this data and continue to work on this. Probably gonna, if it works, then I'm probably gonna use the data to communicate with Pyle next. So I'll be right back.
Unwatch. Stop ignoring. Watch. 583. Notifications. Participating in net mentions. Only receive notifications from this wallets. The word wallet is used to describe a few different things in Ethereum. At a high level, a wallet is a software application that serves as the primary user interface to Ethereum. The wallet controls access to a user's money, managing keys and addresses, tracking the balance, and creating and signing transactions. In addition, some Ethereum wallets can also interact with contracts, such as a 20 token. More narrowly, from a programmer's perspective, the word wallet refers to the system used to store and manage a user's keys. Every wallet has a key management component. For some wallets, that's all there is. Other wallets are part of a much broader category, that of browsers, which are interfaces to Ethereum-based decentralized applications, or dApps, which we will examine in more detail in decentralized_applications_chap. There are no clear lines of distinction between the various categories that are conflated under the term wallet. In this chapter we will look at wallets as containers for private keys, and as systems for managing these keys. Wallet technology overview. In this section we summarize the various technologies used to construct user-friendly, secure, and flexible Ethereum wallet. One key consideration in designing wallets is balancing convenience and privacy. The most convenient Ethereum wallet is one with a single private key and address that you reuse for everything. Unfortunately, such a solution is a privacy nightmare, as anyone can easily track and correlate all your transactions. Using a new key for every transaction is best for privacy, but becomes very difficult to manage. The correct balance is difficult to achieve, but that's why good wallet design is paramount. A common misconception about Ethereum is that Ethereum wallets contain Ether or token. In fact, very strictly speaking, the wallet holds only keys. The Ether or other tokens are recorded on the Ethereum blockchain. Users control the tokens on the network by signing transactions with the keys in their wallet. In a sense, an Ethereum wallet is a keychain. Having said that, given that the keys held by the wallet are the only things that are needed to transfer Ether or tokens to others, in practice this distinction is fairly irrelevant. Where the difference does matter is in changing one's mindset from dealing with the centralized system of conventional banking, where only you and the bank can see the money in your account, and you only need to convince the bank that you want to move funds to make a transaction, to the decentralized system of blockchain platforms, where everyone can see the Ether balance of an account, although they probably don't know the account's owner, and everyone needs to be convinced the owner wants to move funds for a transaction to be enacted. In practice this means that there is an independent way to check an account's balance, without needing its wallet. Moreover, you can move your account handling from your current wallet to a different wallet, if you grow to dislike the wallet app you started out using. Ethereum wallets contain keys, not Ether or tokens. Wallets are like keychains containing pairs of private and public keys. Users sign transactions with the private keys, thereby proving they own the Ether. The Ether is stored on the blockchain. There are two primary types of wallets, distinguished by whether the keys they contain are related to each other or not. The first type is a non-deterministic wallet, where each key is independently generated from a different random number. The keys are not related to each other. This type of wallet is also known as a JBOK wallet, from the phrase, just a bunch of keys. The second type of wallet is a deterministic wallet, where all the keys are derived from a single master key, known as the seed. All the keys in this type of wallet are related to each other and can be generated again if one has the original seed. There are a number of different key derivation methods used in deterministic wallets. The most commonly used derivation method uses a tree-like structure, as described in hierarchical deterministic wallets, BIP32/BIP44. To make deterministic wallets slightly more secure against data loss accidents, such as having your phone stolen or dropping it in the toilet, the seeds are often encoded as a list of words, in English or another language, for you to write down and use in the event of an accident. These are known as the wallet's mnemonic code words. Of course, if someone gets hold of your mnemonic code words, then they can also recreate your wallet and thus gain access to your Ether and smart contract. As such, be very, very careful with your recovery word list. Never store it electronically, in a file, on your computer or phone. Write it down on paper and store it in a safe and secure place. The next few sections introduce each of these technologies at a high level. Non-deterministic, random, wallets. In the first Ethereum wallet, produced for the Ethereum presale, each wallet file stored a single randomly generated private key. Such wallets are being replaced with deterministic wallets because these old-style wallets are in many ways inferior. For example, it is considered good practice to avoid Ethereum address reuse as part of maximizing your privacy while using Ethereum, i.e., to use a new address, which needs a new private key, every time you receive funds. You can go further and use a new address for each transaction, although this can get expensive if you deal a lot with tokens. To follow this practice, a non-deterministic wallet will need to regularly increase its list of keys, which means you will need to make regular backup. If you ever lose your data, disk failure, drink accident, phone stolen, before you've managed to back up your wallet, you will lose access to your funds and smart contract. The Type 0 non-deterministic wallets are the hardest to deal with, because they create a new wallet file for every new address in a just-in-time manner. Nevertheless, many Ethereum clients, including Geth, use a key store file, which is a JSON encoded file that contains a single, randomly generated, private key, encrypted by a passphrase for extra security. The JSON file's contents look like this. The key store format uses a key derivation function, KDF, also known as a password stretching algorithm, which protects against brute force, dictionary, and rainbow table attack. In simple terms, the private key is not encrypted by the passphrase directly. Instead, the passphrase is stretched by repeatedly hashing it. The hashing function is repeated for 262,144 rounds, which can be seen in the key store JSON as the parameter crypto.caveparams.n. An attacker trying to brute force the passphrase would have to apply 262,144 rounds of hashing for every attempted passphrase, which slows down the attack sufficiently to make it infeasible for passphrase of sufficient complexity and length. There are a number of software libraries that can read and write the key store format, such as the JavaScript library Keytherium. The use of non-deterministic wallets is discouraged for anything other than simple tests. They are too cumbersome to back up and use for anything but the most basic of situations. Instead, use an industry standard based HD wallet with a mnemonic seed for back. Deterministic, seeded wallets. Deterministic or seeded wallets are wallets that contain private keys that are all derived from a single master key, or seed. The seed is a randomly generated number that is combined with other data, such as an index number or chain code. See extended public and private keys, to derive any number of private keys. In a deterministic wallet, the seed is sufficient to recover all the derived keys, and therefore a single backup, at creation time, is sufficient to secure all the funds and smart contracts in the wallet. The seed is also sufficient for a wallet export or import, allowing for easy migration of all the keys between different wallet implementations. This design makes the security of the seed of utmost importance, as only the seed is needed to gain access to the entire wallet. On the other hand, being able to focus security efforts on a single piece of data can be seen as an advantage. Hierarchical deterministic wallets, BIP32/BIP44. Deterministic wallets were developed to make it easy to derive many keys from a single seed. Currently, the most advanced form of deterministic wallet is the hierarchical deterministic (HD) wallet defined by Bitcoin's BIP32 standard. HD wallets contain keys derived in a tree structure, such that a parent key can derive a sequence of child keys, each of which can derive a sequence of grandchild keys, and so on. This tree structure is illustrated in HD wallet, a tree of keys generated from a single seed. Figure 1. HD wallet, a tree of keys generated from a single seed. HD wallets offer a few key advantages over simpler deterministic wallets. First, the tree structure can be used to express additional organizational meaning, such as when a specific branch of subkeys is used to receive incoming payments and a different branch is used to receive change from outgoing payment. Branches of keys can also be used in corporate settings, allocating different branches to departments, subsidiaries, specific functions, or accounting category. The second advantage of HD wallets is that users can create a sequence of public keys without having access to the corresponding private keys. This allows HD wallets to be used on an insecure server or in a watch-only or receive-only capacity, where the wallet doesn't have the private keys that can spend the fund. Seeds and mnemonic codes, BIP39. There are many ways to encode a private key for secure backup and retrieval. The currently preferred method is using a sequence of words that, when taken together in the correct order, can uniquely recreate the private key. This is sometimes known as a mnemonic, and the approach has been standardized by BIP39. Today, many Ethereum wallets, as well as wallets for other cryptocurrencies, use this standard and can import and export seeds for backup and recovery using interoperable mnemonic. To see why this approach has become popular, let's have a look at an example. A seed for a deterministic wallet, in hex. A seed for a deterministic wallet, from a 12-word mnemonic. In practical terms, the chance of an error when writing down the hex sequence is unacceptably high. In contrast, the list of known words is quite easy to deal with, mainly because there is a high level of redundancy in the writing of words, especially English words. If insect had been recorded by accident, it could quickly be determined, upon the need for wallet recovery, that insect is not a valid English word and that insect should be used instead. We are talking about writing down a representation of the seed because that is good practice when managing HD wallets. The seed is needed to recover a wallet in the case of data loss, whether through accident or theft, so keeping a backup is very prudent. However, the seed must be kept extremely private, so digital backups should be carefully avoided, hence the earlier advice to back up with pen and paper. In summary, the use of a recovery word list to encode the seed for an HD wallet makes for the easiest way to safely export, transcribe, record on paper, read without error, and import a private key set into another wallet. Best practices. As cryptocurrency wallet technology has matured, certain common industry standards have emerged that make wallets broadly interoperable, easy to use, secure, and flexible. These standards also allow wallets to derive keys for multiple different cryptocurrencies, all from a single mnemonic. These common standards are mnemonic code words, based on BIP39, HD wallets, based on BIP32, multipurpose HD wallet structure, based on BIP43, multi-currency and multi-account wallets, based on BIP44. These standards may change or be obsolete by future developments, but for now they form a set of interlocking technologies that have become the de facto wallet standard for most blockchain platforms and their the standards have been adopted by a broad range of software and hardware wallets, making all these wallets interoperable. A user can export a mnemonic generated in one of these wallets and import it to another wallet, recovering all keys and addresses. Some examples of software wallets supporting these standards include, listed alphabetically, Jax, MetaMask, MyCrypto, and MyEtherWallet, Mu. Examples of hardware wallets supporting these standards include Keepgate, Ledger, and Trezor. The following sections examine each of these technologies in detail. If you are implementing an Ethereum wallet, it should be built as an HD wallet, with a seed encoded as a mnemonic code for backup, following the BIP32, BIP39, BIP43, and BIP44 standards, as described in the following section. Mnemonic code words, BIP39. Mnemonic code words are word sequences that encode a random number used as a seed to derive a deterministic wallet. The sequence of words is sufficient to recreate the seed, and from there recreate the wallet and all the derived keys. A wallet application that implements deterministic wallets with mnemonic words will show the user a sequence of 12 to 24 words when first creating a wallet. That sequence of words is the wallet backup, and can be used to recover and recreate all the keys in the same or any compatible wallet application. As we explained earlier, mnemonic word lists make it easier for users to back up wallets, because they are easy to read and correctly transcribe. Mnemonic words are often confused with brain wallets. They are not the same. The primary difference is that a brain wallet consists of words chosen by the user, whereas mnemonic words are created randomly by the wallet and presented to the user. This important difference makes mnemonic words much more secure, because humans are very poor sources of randomness. Perhaps more importantly, using the term brain wallet suggests that the words have to be memorized, which is a terrible idea, and a recipe for not having your backup when you need it. Mnemonic codes are defined in BIP39. Note that BIP39 is one implementation of a mnemonic code standard. There is a different standard, with a different set of words, used by the Electrum Bitcoin wallet in predating BIP39. BIP39 was proposed by the company behind the Trezor hardware wallet and is incompatible with Electrum's implementation. However, BIP39 has now achieved broad industry support across dozens of interoperable implementations and should be considered the de facto industry standard. Furthermore, BIP39 can be used to produce multi-currency wallets supporting Ethereum, whereas Electrum seeds cannot. BIP39 defines the creation of a mnemonic code and seed, which we describe here in 9 steps. For clarity, the process is split into 2 parts. Steps 1 through 6 are shown in generating mnemonic words and steps 7 through 9 are shown in from mnemonic to seed. Generating mnemonic words. Mnemonic words are generated automatically by the wallet using the standardized process defined in BIP39. The wallet starts from a source of entropy, adds a checksum, and then maps the entropy to a word list. Create a cryptographically random sequence S of 128 to 256 bits. Create a checksum of S by taking the first length of S divided by 32 bits of the SHA-256 hash of S. Add the checksum to the end of the random sequence S. Divide the sequence and checksum concatenation into sections of 11 bits. Map each 11-bit value to a word from the predefined dictionary of 2048 words. Create the mnemonic code from the sequence of words, maintaining the order. Generating entropy and encoding as mnemonic words shows how entropy is used to generate mnemonic word. Mnemonic codes, entropy and word length shows the relationship between the size of the entropy data and the length of mnemonic codes and words. Table 1. Mnemonic codes, entropy and word length. Entropy, bits. Checksum, bits. Entropy plus checksum, bits. Mnemonic length, words. 128.4. 132.12. 165, 165.15, 192.6, 198.18, 224.7, 231.21, 256.8, 264.24. Figure 2. Generating entropy and encoding as mnemonic words. From mnemonic to seed. The mnemonic words represent entropy with a length of 128 to 256 bit. The entropy is then used to derive a longer, 512-bit, seed through the use of the key stretching function PBKDF2. The seed produced is used to build a deterministic wallet and derive its key. The key stretching function takes 2 parameters, the mnemonic and a salt. The purpose of a salt in a key stretching function is to make it difficult to build a lookup table enabling a brute force attack. In the BIP39 standard, the salt has another purpose. It allows the introduction of a passphrase that serves as an additional security factor protecting the seed, as we will describe in more detail an optional passphrase in BIP39. The process described in steps 7 through 9 continues from the process described in the previous section. The first parameter to the PBKDF2 key stretching function is the mnemonic produced in step 6. The second parameter to the PBKDF2 key stretching function is a salt. The salt is composed of the string constant mnemonic concatenated with an optional user-supplied passphrase. PBKDF2 stretches the mnemonic and salt parameters using 2048 rounds of hashing with the HMAC SHA-512 algorithm, producing a 512-bit value as its final output. That 512-bit value is the seed. From mnemonic to seed shows how a mnemonic is used to generate a seed. Figure 3. From mnemonic to seed. Note. The key stretching function, with its 2048 rounds of hashing, is a somewhat effective protection against brute force attacks against the mnemonic or the passphrase. It makes it costly, in computation, to try more than a few thousand passphrase and mnemonic combinations, while the number of possible derived seeds is vast, 2,512, or about 10,154, far bigger than the number of atoms in the visible universe, about 1,080. Tables hashtag mnemonic underscore 128 underscore no underscore pass, hashtag mnemonic underscore 128 underscore W underscore pass, and hashtag mnemonic underscore 256 underscore no underscore pass show some examples of mnemonic codes and the seeds they produce. Table 128-bit entropy mnemonic code, no passphrase, resulting seed. Entropy input, 128 bits. 0C1E24E59177790E297E14D4, mnemonic, 12 words. Army van defense, passphrase. None, seed, 512 bits. 5B56, table 3. Entropy, mnemonic, Army van defense, pass, seed, table, pass, none. Seed, 3269, optional pass. The BIP39 standard allows the use of an optional passphrase in the derivation of the seed. If no passphrase is used, the mnemonic is stretched with a salt consisting of the constant string mnemonic, producing a specific 512-bit seed from any given mnemonic. If a passphrase is used, the stretching function produces a different seed from that same mnemonic. In fact, given a single mnemonic, every possible passphrase leads to a different seed. Essentially, there is no wrong passphrase. All passphrases are valid and they all lead to different seeds, forming a vast set of possible uninitialized wallet. The set of possible wallets is so large, 2,512, that there is no practical possibility of brute forcing or accidentally guessing one that is in use, as long as the passphrase has sufficient complexity and length. There are no wrong passphrases in BIP39. Every passphrase leads to some wallet, which unless previously used will be empty. The optional passphrase creates two important features. A second factor, something memorized, that makes a mnemonic useless on its own, protecting mnemonic backups from compromise by a thief. A form of plausible deniability or Duress wallet, where a chosen passphrase leads to a wallet with a small amount of funds, used to distract an attacker from the real wallet that contains the majority of funds. However, it is important to note that the use of a passphrase also introduces the risk of loss. If the wallet owner is incapacitated or dead and no one else knows the passphrase, the seed is useless and all the funds stored in the wallet are lost for it. Conversely, if the owner backs up the passphrase in the same place as the seed, it defeats the purpose of a second factor. While passphrases are very useful, they should only be used in combination with a carefully planned process for backup and recovery, considering the possibility of errors surviving the owner being able to recover the cryptocurrency. Working with mnemonic codes. BIP39 is implemented as a library in many different programming languages. For example, Python mnemonic. The reference implementation of the standard by the Satoshi Labs team that proposed BIP39 in Python. Consensi/Eth wallet. Lightweight JS Ethereum wallet for nodes and browser with BIP39. npm/BIP39. JavaScript implementation of Bitcoin BIP39. Mnemonic code for generating deterministic key. There is also a BIP39 generator implemented in a standalone web page. A BIP39 generator is a standalone web page, which is extremely useful for testing and experimentation. The mnemonic code converter generates mnemonics, seeds, and extended private keys. It can be used offline in a browser or accessed online. Figure 4. A BIP39 generator is a standalone web page, creating an HD wallet from the seed. HD wallets are created from a single root seed, which is a 128-256- or 512-bit random number. Most commonly, the seed is generated from a mnemonic as detailed in the previous section. Every key in the HD wallet is deterministically derived from this root seed, which makes it possible to recreate the entire HD wallet from that seed in any compatible HD wallet. This makes it easy to export, backup, restore, and import HD wallets containing thousands or even millions of keys by transferring just the mnemonic from which the root seed is derived. HD wallets, BIP32, and paths, BIP43/44. Most HD wallets follow the BIP32 standard, which has become a de facto industry standard for deterministic key generation. We won't be discussing all the details of BIP32 here, only the components necessary to understand how it is used in wallets. The main important aspect is the tree-like hierarchical relationships that it is possible for the derived keys to have, as you can see in HD wallet, a tree of keys generated from a single seed. It's also important to understand the ideas of extended keys and hardened keys, which are explained in the following sections. There are dozens of interoperable implementations of BIP32 offered in many software libraries. These are mostly designed for Bitcoin wallets, which implement addresses in a different way, but share the same key derivation implementation as Ethereum's BIP32 compatible wallet. Use one designed for Ethereum, or adapt one from Bitcoin by adding an Ethereum address encoding library. There is also a BIP32 generator implemented as a standalone web page that is very useful for testing and experimentation with BIP30. The standalone BIP32 generator is not an HTTPS site. That's to remind you that the use of this tool is not secure. It is only for testing. You should not use the keys produced by this site with real fun. Extended public and private keys. In BIP32 terminology, keys can be extended. With the right mathematical operations, these extended parent keys can be used to derive child keys, thus producing the hierarchy of keys and addresses described earlier. A parent key doesn't have to be at the top of the tree. It can be picked out from anywhere in the tree hierarchy. Extending a key involves taking the key itself and appending a special chain code to it. A chain code is a 256-bit binary string that is mixed with each key to produce child keys. If the key is a private key, it becomes an extended private key distinguished by the prefix XPRV. An extended public key is distinguished by the prefix SPUB. A very useful characteristic of HD wallets is the ability to derive child public keys from parent public keys, without having the private keys. This gives us two ways to derive a child public key, either directly from the child private key, or from the parent public key. An extended public key can be used, therefore, to derive all of the public keys, and only the public keys, in that branch of the HD wallet structure. This shortcut can be used to create very secure public key only deployments, where a server or application has a copy of an extended public key, but no private keys whatsoever. That kind of deployment can produce an infinite number of public keys and Ethereum addresses, but cannot spend any of the money sent to those addresses. Meanwhile, on another, more secure server, the extended private key can derive all the corresponding private keys to sign transactions and spend them. One common application of this method is to install an extended public key on a web server that serves an e-commerce application. The web server can use the public key derivation function to create a new Ethereum address for every transaction, example for a customer shopping cart, and will not have any private keys that would be vulnerable to theft. Without HD wallets, the only way to do this is to generate thousands of Ethereum addresses on a separate secure server and then preload them on the e-commerce server. That approach is cumbersome and requires constant maintenance to ensure that the server doesn't run out of keys, hence the preference to use extended public keys from HD wallet. Another common application of this solution is for cold storage or hardware wallets. In that scenario, the extended private key can be stored in a hardware wallet, while the extended public key can be kept online. The user can create receive addresses at will, while the private keys are safely stored offline. To spend the funds, the user can use the extended private key in an offline signing Ethereum client, or sign transactions on the hardware wallet device. Hardened child key derivation. The ability to derive a branch of public keys from an extended public key, or SPUB, is very useful, but it comes with a potential risk. Access to an SPUB does not give access to child private keys. However, because the SPUB contains the chain code used to derive child public keys from the parent public key, if a child private key is known, or somehow leaked, it can be used with the chain code to derive all the other child private keys. A single leaked child private key, together with a parent chain code, reveals all the private keys of all the children. Worse, the child private key together with a parent chain code can be used to deduce the parent private key. To counter this risk, HD wallets use an alternative derivation function called hardened derivation, which breaks the relationship between parent public key and child chain code. The hardened derivation function uses the parent private key to derive the child chain code, instead of the parent public key. This creates a firewall in the parent/child sequence, with a chain code that cannot be used to compromise a parent or sibling private key. In simple terms, if you want to use the convenience of NSPUB to derive branches of public keys without exposing yourself to the risk of a leaked chain code, you should derive it from a hardened parent, rather than a normal parent. Best practice is to have the level 1 children of the master keys always derived by hardened derivation to prevent compromise of the master keys. Index numbers for normal and hardened derivation. It is clearly desirable to be able to derive more than one child key from a given parent key. To manage this, an index number is used. Each index number, when combined with a parent key using the special child derivation function, gives a different child key. The index number used in the BIP32 parent-to-child derivation function is a 32-bit integer. To easily distinguish between keys derived through the normal, unhardened, derivation function versus keys derived through hardened derivation, this index number is split into two ranges. Index numbers between 0 and 231 to 1, 0x0 to 0x7 FFFFFF, are used only for normal derivation. Index numbers between 231 and 232 to 1, 0x8 0 0 0 0 0 0 0 to 0xFFFFFF, are used only for hardened derivation. Therefore, if the index number is less than 231, the child is normal, whereas if the index number is equal to or above 231, the child is hardened. To make the index numbers easier to read and display, the index numbers for hardened children are displayed starting from 0, but with a prime symbol. The first normal child key is therefore displayed as 0, whereas the first hardened child, index 0x8 0 0 0 0 0 0 0, is displayed as 0. In sequence, then, the second hardened key would have index of 0x8 0 0 0 0 0 0 1 and would be displayed as 1, and so on. When you see an HD wallet index I, that means 231 plus I HD wallet key identifier, path. Keys in an HD wallet are identified using a path naming convention, with each level of the tree separated by a slash, character. See HD wallet path examples. Private keys derived from the master private key start with M. Public keys derived from the master public key start with M. Therefore, the first child private key of the master private key is M/0. The first child public key is M/0. The second grandchild of the first child is M/0/1, and so on. The ancestry of a key is read from right to left, until you reach the master key from which it was derived. For example, identifier M/X/Y/Z describes the key that is the ZTH child of key M/X/Y, which is the YTH child of key M/X, which is the XTH child of M. Table 5. HD wallet path examples. HD path. Key described. M/0. The first, 0, child private key of the master private key, M. M/0/0. The first grandchild private key of the first child, M/0. M/0/0. The first normal grandchild of the first M/1/. The first grandchild private key of the second child, M/1. M/23/17/0/0. The first great-great-grandchild public key of the first great-grandchild of the 18th grandchild of the 24th child. Navigating the HD wallet tree structure. The HD wallet tree structure is tremendously flexible. The flip side of this is that it also allows for unbounded complexity. Each parent extended key can have 4 billion children, 2 billion normal children and 2 billion hardened children. Each of those children can have another 4 billion children, and so on. The tree can be as deep as you want, with a potentially infinite number of generations. With all that potential, it can become quite difficult to navigate these very large trees. 2 BIPs offer a way to manage this potential complexity by creating standards for the structure of HD wallet tree. BIP 43 proposes the use of the first hardened child index as a special identifier that signifies the purpose of the tree structure. Based on BIP 43, an HD wallet should use only one level 1 branch of the tree, with the index number defining the purpose of the wallet by identifying the structure and namespace of the rest of the tree. More specifically, an HD wallet using only branch M/I/ is intended to signify a specific purpose, and that purpose is identified by index number I. Extending that specification, BIP 44 proposes a multi-currency multi-account structure signified by setting the purpose number to 44. All HD wallets following the BIP 44 structure are identified by the fact that they only use one branch of the tree, M/44/star. BIP 44 specifies the structure as consisting of 5 predefined tree levels. M/purpose/coin_type/account/change/address_index. The first level, purpose, is always set to 44. The second level, coin_type, specifies the type of cryptocurrency coin, allowing for multi-currency HD wallets where each currency has its own subtree under the second level. There are several currencies defined in a standards document called SLIP 0044. For example, Ethereum is M/44/60, Ethereum Classic is M/44/61, Bitcoin is M/44/0, and testnet for all currencies is M/44/1. The third level of the tree is account, which allows users to subdivide their wallets into separate logical sub-accounts for accounting or organizational purposes. For example, an HD wallet might contain 2 Ethereum accounts, M/44/60/0 and M/44/60/1. Each account is the root of its own subtree. Because BIP 44 was created originally for Bitcoin, it contains a quirk that isn't relevant in the Ethereum world. On the fourth level of the path, change, an HD wallet has 2 subtrees, one for creating receiving addresses and one for creating change addresses. Only the receive path is used in Ethereum, as there is no necessity for a change address like there is in Bitcoin. Note that whereas the previous levels used hardened derivation, this level uses normal derivation. This is to allow the account level of the tree to export extended public keys for use in a non-secured environment. Usable addresses are derived by the HD wallet as children of the fourth level, making the fifth level of the tree the address. For example, the third receiving address for Ethereum payments in the primary account would be M/44/60/0/0/2. BIP 44 HD wallet structure examples shows a few more examples. Table 6. BIP 44 HD wallet structure examples. HD path. Key conclusions. Wallets are the foundation of any user-facing blockchain application. They allow users to manage collections of keys and addresses. Wallets also allow users to demonstrate their ownership of Ether and authorize transactions by applying digital signatures, as we will see in TX_chapter.
gonna put another hour and then I'll take another break. And it looks like it's wrong here. Like it's getting the position, but it's not getting on all of the actions. I wanna understand why. As here it has the position, but on this one it doesn't. Let's see, actions. Oh, it's because of this. So I can just put here position and then let me think. Because the thing is, I don't want to put this stuff again there. Player name, player. And then if I access by the players, I have to loop again. It's not very good. But I think it's not necessary actually to put on the actions because I can just get it from like the player object. So the way that I think it works is that each player has the actions. Yeah, so it's not necessary because here is the position. And I only need this position one time. So I don't need to put it here. But that's the thing that I'm thinking of. It's like, it feels that this is wrong because it could be more efficient. Because here is just repeated stuff. Like why I'm putting player here if all of the actions are from this player. So I think I'm gonna remove the player, the type, and then here I'm gonna change to actual name so that it's easier to understand. And maybe put round here. Where I'm using the current rounds. Place here. Yeah, so here I put it. I think this way is gonna be better because then it's easier to understand. Here is gonna be rounds. Like this, and then here action. And so otherwise I think it's kind of confusing when and I'm thinking if there's any other thing that I want to do before running that again. And then after I run, I'm gonna take these objects and this data, and then I'm gonna replace this with the new one. And then I'm gonna look at this data, and I'm gonna think about how I can loop over it to get the information. I'm gonna do it on this file, like load the JSON file and then loop over the players or the... And the thing is that like there's another layer here that I'm missing because each one of these is a list, I think. Because each one of them is a hand. So I loop over this, and then I access the players, and then loop over the players to get the information of each hand. I think the first thing that I'm gonna do is probably the board cards. Create a hash map or a counter for the checking the frequency of the boards. Yeah, there are all kinds of things that I can do then, once I have the data, once I have the structure. Oh, the first thing that I probably should do is actually the actions, figure out how to create an algorithm to give me the line based on the sequence of actions, based on each round. That's what it's gonna do. And that's what I have to think about here, if it makes sense, the way that I'm doing now. Because for each player, there is gonna be the list of actions for that player, I think, in the round. And player 1, cut off. And the actions 0, player 1, player 1. Then jumps to player 3. So for each one, I'm getting the actions only for that player on the rounds. Yeah, so I think I have to go over all of them. Let me think. I have to see if the number is correct. A 0, action number 2. Yeah, so I think it is correct. So the number is gonna be the absolute number. Because the other one is action 7. So it only shows the actions that the player did, and the number is the sequence. So I need to figure out how to go from the sequence to a line based on the rounds. Which is not that hard to do, but it's gonna be tricky, I think. Then once I figure out how to do this algorithm, then I'll think about the rest, because then once I have the lines, and the boundaries are going to be based on the rounds, because obviously each bet on a specific round is going to be considered as a raise if it is not the first bet. And then 0 is check, and so I think I'm not missing anything. I think this way is probably the final way. So I'm gonna put it on the data file. Oh, actually, let me think. I already have the data on the data show. I forgot now. Yeah, I think this is already the way that I want, so I can just use this one. Oh, there's the game that I didn't put there. So the game is the stuff that I'm gonna use. I'm gonna copy this, No actions. Where's the difficult part is figuring out where the end is. I think it's here. As players. So. Oh, actually, when he gets to the board cards now. Yeah, here. So this is one hand, I think. Yeah, it's gonna be very tricky. I think I was gonna change something and run again, but then I forgot. Or maybe it was just the position there that I decided that it doesn't matter. What makes this difficult is that there's so many nested things. I think I'm gonna run again and then save on the data. Oh yeah, I was gonna remove the player information here. This information. Because it doesn't matter. Like all the actions are... So I'm gonna keep true different... I'm gonna keep the data true and the data. Because that way, in case it matters, then I can use either one. But I think the only thing that matters is the sum and the actual number. The sum is the bat size and the actual number is the sequence. That's why I was gonna run this again. And he was forgetting something. I'm just gonna run and save on the data now. Okay, so obviously I'm missing something. So what's up with that? Maybe it's because I changed here. Why is not working now? I think I'll leave the round as just a number, and then the action, I put the number of the action. See if that's the what's wrong there. But I think it might be something else. I think it might be the name of the player here for some reason. Because this name should be outside of the actions. That's the thing. Let's see if it works now. It's data. Alright, that's weird. Oh, it is definitely this thing, but I don't understand why. I'm probably missing something. Yeah. Why does this need to have the player here? It's probably because of this check. Player current sense. So it's getting the name of the player equals action player. Action is not in player. So the question is, do I need this check here? I think yes, because of that's the problem. Is the order of the thing. Because you don't know which order is gonna get the actions, I think. So in order to know which action comes from each player, you have to put the name to make this check. That's the problem. Yeah, I think I'm gonna leave it like this then. Just remove the type, I think. Yeah, just remove the type and leave the player name, because it's easier. I don't want to think about. Maybe in the future I can think about how to remove this and change the checks here. I think I'm gonna leave it like this and the fuck? So the problem here is that you would have the other hands, should be an object like this. And then here. Yeah, so it's missing the thing here. What's wrong now? The object outside. And there we go. This is gonna be difficult to figure out. think it's just JSON.loads, but I wanna make sure. And then I'm gonna loop over the data and the object there. There's gonna be this game, which is gonna have all the hands. So the first thing that I'm gonna do, I think, is create a dictionary and just get the bards data, hands, board cards, and then create a counter. I think I can do with Python. I don't remember. I think, yeah, from counter imports counter. I don't remember. Maybe it's the other way around. I think that doesn't make sense. Should be the other way around. I'm just gonna search for this. Oh yeah, I wanna remember the difference between loads and load. String and then, so it's probably load. You can obviously try both. Yeah, collections. Yeah, there we go. I think that's how you use it. I saw this when I was doing one of the articles, but I don't remember really well how to use this stuff. I know that it's like a dictionary that is gonna keep track of the frequencies. It's one of the algorithms that I saw that use this stuff. So I don't even need to loop, maybe, but I need to loop to get the stuff. Yeah, I need to create a list out of the bards first. So to unpack from this stuff from the dictionary, I think. And then I just create the counter of the list. Yeah. And then here put bars and prints board frequency. So I think this should give me the frequency, a dictionary with the bards and the how often they show up in the list. And then maybe I'm probably gonna use that to get only the, I can create filters based on that to only get those bars, the hands that have those bars. So I get this counter again, and then I use a condition, like I sort or a filter Not sure if filter works. Like to shrink the dictionary so it's only up to a certain amount, a certain frequency, and then based on that I can create the hands or the simulations based on the bars that happen most often. And then I'm gonna use that to get the information as well, the other information from the hand. So I can create a condition. I don't need to no, I need to filter to get the threshold of the frequency that I want. So create the counter, then create the threshold of the frequency. With that new dictionary, then I can use to check for the conditions. And then I can make a if statement to get the information for the other hands. Or I can filter, but the filter is not gonna work because it's a dictionary instead of a list. Or maybe it does work, but no, I don't think. So I think before I think about that, the first thing that I'm gonna think about now is how to translate the rounds and the actions into a line. So I think the only conditions that matter is the because yeah, I think like I have a list of actions, so the only thing that matters is the boundaries of the rounds. And no, but that's the problem, because the round one it becomes an issue. Because there's an arbitrary amount of actions in the first round, so in the second round, it's like on the first round I can use the simple rule that the first action, like the first betting action is a bet, and all of the other zeros are checks, and then anything else after that first bet is a raise. But then the problem is that on the next round, then I still have the sequence though, like I still know the order from the previous round. But I need to maintain the order that I constructed on the first round to build the second round, I think. Yeah, because what I'm trying to extract is whether or not, like, which player is out of position and which player is in position. So let me think. Because like it seems that it's simple, but it's kind of confusing, because the way that I think about it, about hands, is using those lines now. It's like the way that we talk about it usually is like check, then bats, check, for example. And this means that both players check on the flop, then one player bats and the other, and then it's a check on the river as well. So the question is how to translate these lines, because the problem is that there is an infinite. Then if you put raise, it puts an R here, but then there's an infinite amount of things that can happen on each one. So I'm trying to think, how do I get the sequence and translate into lines so it's easier to think about when building the simulation. But do I need to do that? That's not I think I need, because I need to populate the bets that are on the simulation. But I think it's actually easier. I can just get by rounds, because like the first round I can just ignore, because just posting the blinds. And then the other ones I get by rounds. So each round, because in the simulation it doesn't matter the order, because you're gonna evaluate all of the possible bets. So here, you just like you can put any amount of bets. Yeah, the only thing that matters is the donk, or the donking. It matters. That's the thing. So I think it's better if I create the algorithm anyway to get the line. And for the raise as well, because I need to know if it's a bet or a raise. So it does matter. Yeah, but now it looks better, I think. So let me think. I guess I can run this stuff already. The other thing while I think about this. Why is it giving me error? So, oh yeah, so it is. I think I need to load the file first. That's the thing. Now let me run this and see if it works. It seems like it's not working, or maybe it's taking a long time to read the file. This should print the hands. Yeah, so let me think. I need to translate a list of actions. The first thing that I need to do is get all the actions for all the players. So I need to access this players here for each hand. So loop over the players. And I think I have to do an nested for loop, because I need to loop through all the hands. So I don't think I can simplify more than that. And there's no way to avoid the nested for loop. Yeah, I think there isn't. For turn and river, I think it's simple. You just get the length of the string, and then based on the order that I put there, I can use the index to get the flop. But it's probably gonna be, yeah, I have to put the length of the string, because if there's more, then it's gonna be messed up if I just get from the beginning. This looks like it's working. Let me think. So yeah, I loop over the players. I access first. I loop over the hands, like I'm doing here. Then on the hands is gonna be players, hand, players. And then I loop over hand players, and then I get the action. And that's the parts, because each one is gonna be a dictionary. So how I'm gonna access the rounds here and get in the most efficient way possible, get all the actions for all the players. Because the rounds are gonna be the same. And what I wanna get is the sequence of actions and bets. And once I have that, then yeah, what I'm gonna do here after these runs is just I comment everything out, and then I'm gonna put a flag variable and just do a couple of iterations. And I think once I figure out these algorithms, like everything that I want to do, then I'm going to encapsulate all of them into functions and maybe create a class to put all of them. But I think for testing like this, it's better to do it like this because it's easier to run each thing and it's easier to think about. And then once I figured out how to get each specific thing that I want from like each specific thing to build a simulation from the data here, like once I have everything, then I'm going to focus on the solver parts, on trying to understand how to run the commands on the solver and what kind of formats will. Well, the other thing is the ranges. I think that's one of the big things as well. I need to figure out how to get the ranges first. But I think that's easy because I'm getting the hands for each player. Yeah, pocket cards. So I can just filter. It's not that hard, I think. I can just do the nested for loop and then I do the same thing that I'm doing here for the bards. I just put all the pocket cards on the... and based on position. I create a dictionary based on the position and then I put the cards there. I create a counter for the... like the position is going to be the key and then the value is going to be a counter that contains the hand and the frequency. So, but I'm going to focus on the actions first. And so what I'm going to do is put this count here. Maybe I should just wait to everything run. To do this other stuff. It looks like it finished. Yeah, so I can't see all of them. But I think it's working. So I have the bars and the frequency here. And obviously what I can do is sort and then filter. I think there's some function that I'm forgetting that can... like is gonna give me the threshold for the ones. I think filter does it. I just filter and then puts the condition for an arbitrary number. So... but then I wonder if I can... I'll think about this later. I'm gonna focus on the action first. The actions. This is Alt, Shift, and up arrow to move the lines. And so here I think I have to do the same thing that I did here and then loop over the... What? Oh, it changed here. Now each player is going to have actions. And the problem is that the actions are dictionary. Like, I don't want to do another loop. That's the thing. Because then if I loop over each one, it feels like very inefficient. And the biggest concern I have here is the, like, this is the problem, is because it's hard to think about the structure of this data here when I'm not really sure what kind of information I'm gonna get at the end. So maybe the best way to do it would probably be to figure out the solver part first, do it with one, and then reverse through the data. So maybe it's a mistake to start like this, because now it might make a lot more inefficient. But then the problem is that I don't want to change like everything from this script here again. So I get another data so that these algorithms for the analysis become better. So let me see if I can think about a way to get all the actions without looping. But I think there's not gonna be, because it's gonna be... yeah, it's gonna be a nightmare. Like, there's a list, each round is a list with the objects as well. To make it more complicated. I could do, like, I'm gonna have to create other functions to unpack this probably better, and then I can just call the function past the arguments. But it's annoying to think about. Maybe I can do another way actually. I can just... but I think I have to loop anyway to get all the actions. So there's no way to avoid that. And the problem is that I think it would be more efficient, obviously, if I got like all the actions in an array instead. But then, like, you don't have information of the round then. And in the way that is here, each player is... like, each player has actions. Maybe it would be better if each action had players. If it was actions here instead of players, and then there was the round. I'm not sure if that will make it better either. I think I should worry first, though, to make this work, and then I think about... it's better to do like the brute force solution first, and then I think about optimizing after. I think then should just be stuck, because it's very difficult to think about what's the best way to structure this. Because then I'm gonna have to go here, and then I have to remember that it's line by line, how to restructure everything. Like all of the flow of information here, so that I have another data structure here. So at the end I have an algorithm that changes. That is faster to get the sequence of actions. What I'm thinking about now is why not create another dictionary on the JSON file? Like with just information from the actions. So then instead of making the actions part of the players here, I make another thing. Yeah, but then it becomes an issue because I have to remember that each hand has this information. So I can't just have the actions, because then it becomes really hard to know exactly. Like obviously I can use the index and put the actions, but then it's not the same as well because there might be more actions for each hand, so the indexes are not gonna match. If I just put this outside on a different list outside. As the thing is that the reason why it doesn't feel right is because I'm repeating the number of rounds for each one. That's why. It would be much better if there was only one action and then the round and then all of the actions for the round. But then you would have to repeat anyway because each player has to have like the actions. So here's more the actions of each player for the round. So let me think. So I think I can't avoid this. I'm gonna have to do 3 for loops, which is really bad. There's O and 3 and to the third. It's really slow. I'm looping over the hands, then over the players. Then for each player, I would get the action, and the action is the dictionary. Pair. I think this is actions. It seems to have no effect. The thing is that I think the rounds are gonna exist for all of them. Oh no, this one only has the first round. This one has 0. So I can just make a condition, obviously, to check. Let's see. And the thing is, these kinds of things, like, there's nothing I can do to... Like, I just have to spend a lot of time thinking about it to see if there's any other way. But it seems like from here is very straightforward. It's more of a question of how to optimize this than like a question of how I'm gonna do it. Because I think it's really easy. Yeah, maybe I should be thinking about the rounds where I'm gonna do it. The only thing that I need to classify is the donk, and then after that, like, everything else. Yeah, but it's kind of complicated because I need to cache the... I need to know which player batted, which player called. That's the thing as well, that it's not either gonna be bat or raise, there's gonna be calls as well. So it is actually hard, actually, because I need to figure out, like, if the bat is the same size, I can make that it is a call. So if it checks first, then it's out of position, maybe. So I don't need to know if it's out of... Oh, actually I do need to know. Because the simulation here, it's in position, out of position. So if checks first, the player that checks first in the rounds is out of position. Yeah, but that's the thing. Actually, it's very complicated. Because depending on which range here, which position, what position it is, like, it's gonna change who is out of. Let's say there's 3 players in the hand. So if let's say small blind, big blind, and button. If small blind checks and big blind checks, and then button bets, I can't make the condition that if a player checks is out of position. Because then big blind, small blind might call the bets, and then big blind raises, for let's say, then button folds and small blind calls. Then in this case, big blind would be out of position first because it checked first, but now it is in position against the small blind. So I can't just make a condition that if the player checks is out of position, because it depends on the actions of the other players. Because the bets can vary each time, is actually very hard to think about it. Let me first think how I'm gonna get. So actions, and then I get the rounds here. But I have to check if the round exists. I think this would work. And this is a list, so I have to loop over this. And I would need the player. I already have the player here. And so player name. Would be the player. Just gonna put this so that it stops giving me the warning. And so I'm getting, because the actions are always going to be from the same player, I can just get this name instead. Which doesn't make any difference, because I can't get it outside, I think. Oh, let me think. Yeah, so the question is what I'm gonna do with the actions. I wanna get the number of them from here. So I think inside of the loop I just get the number. Get the number and the sum. So it does make a difference, because then I can get the name outside of the loop, the other loop. I think round 0 doesn't matter. It's just posting the blinds. Or maybe I should remove round 0 from the actions, like on here. It's not gonna matter. The only reason why I thought it mattered is because of forgetting the position, but the way that I'm doing now, it doesn't matter. It's pretty much the same check. But I think I have to put it, otherwise it's gonna fail on the other parts. On the action, because of the whole line sequence thing. And actually the number of the actions is, it does take into account the 0, so I think it does matter. That's another thing that is complicated, because sometimes you're gonna have 2 actions, sometimes you're gonna have more actions on the... But I think I can just discard them. I can just subtract or start counting from the 0. 0 is just posting blinds, and then 1 is pre-flop. And then the 2 is flop, 3 is turn, 4 is river. I think I need to make the check as well, because not all of the players are gonna have, so seems kind of redundant, but I think I need to do it. And then I need to loop here as well. That's the thing that I'm concerned about. That's why I'm thinking so much, because I know it's gonna be really slow, because there's gonna be several different loops, like up to 4 different loops for each round, and then those loops are nested inside of these ones, so it's gonna be really slow. Which makes me think it might be worth it to just think about a way to restructure this, so I don't have to do it like that. If I could put all the actions together and just put one action for each hand, it would be better. So put the actions outside of the players here. Put it here. Actions. And then I put the rounds only. Yeah, that would be a lot better. So I think it is worth just spend the time thinking about this. Like, this sounds a lot better. Like, put the actions here, and then I just put one round for each. It's gonna be far more efficient. And then on each round, there's the... like, all of the possible actions. As dictionary, but... yeah. Get the point. And because here I'm putting the player name anyway, to append to the round. Let me think. So what I have to change is this line here. So this is the thing that is going on the action. So there. So like, if I change this thing here, it works, I think. I don't understand this actually. Oh, it's coming for you. I should player. Yeah, because this object here, not this thing here. This action, so it's accessing this part here. And this is the part, I think I don't need to make this check. Instead of doing this, I just append our player in current. He's looping over the players. And the thing is that is doing the loop here. It's confusing because I don't know it's hard to think about the order of things. So obviously if I move this stuff from here to the other level, I don't know if it's gonna mess up on the order that is reading the lines to get the information. That's why it's confusing. So here is looping through the players. So like it's supposed to get to this line at the end of the round when it has all the actions already and all the players in this thing here. And then for each player is creating an object. It's creating the current round, which is gonna be the key value pair of the thing. And the thing is, let me think. Because I think I can do this outside. I just put if the current hand actions like do the same thing. If current round not in current hand actions, then I put it. Like if not anything. I'm not sure if this would work. I can initialize here, I don't need to do this stuff. They'll do actions here. And that's the problem. It has to be a dictionary, I think, to get the rounds. Or current hand actions. And then I'll change here. I think this check is fine. Now the other thing that I'm thinking about it is I don't need to put the player on the actions. But it is better if I do it like that now, because then the actions are going to be separated. So, and before I didn't need to put the, I could just put this stuff outside of here and not include on the actions. But now, since the way that I'm thinking about it is putting the actions outside here, then it's better if each action has the name of the player, because then I know, like, based on the rounds. So I'm gonna leave it there. So the idea is to create only one action object per hand. Outside of here, put it here. And then that's gonna contain each round, and then on each round is gonna have all the actions. That's what I want to do, because that way I can only loop once there per hand. It's going to be a lot easier to get the information. So players and current hand players. So here the thing that's confusing me is this thing here, because here is looping through all of the hands, so through all of the players, so it means that it has all the players. So yeah, so now it's checking to see the action. So I think the only thing that I need to change is this thing here, where I just put, instead of here, I put current hand. And And I think this works because each hand is different. So. And then I don't need this stuff. Action's not in player. Then I keep this check to see if the action is from the player. Then I create, and then player action, which is this thing. I actually, let me think. Yeah, it has to be current to hand actions. Then current rounds, then append action. Yeah, let's run. I think this way is gonna work. So what I'm doing again is translating, like moving this stuff from here to the top. And then I'm only gonna have like one round for each, and then in each round it's gonna contain all the actions for all the players. And then I can differentiate because I'm still keeping the name of the player with each action. So I think I'm gonna leave on the data again, like rewrite the stuff. And let's let me double check to see if I'm not missing anything before I run this and go get something to eat. So I'm looping over the players of the current hand, and I'm checking to see if the name is equal to this one. Player name. Oh, current hand actions, which is the object for the hand. Then I create the rounds, and the round is gonna be a list of actions. So I'm just moving the object on the outer layer. I wonder if there's any way that I can do here, but I think I can't because there's gonna be multiple actions, so I have to do a list. Like there's nothing I can do about it. Current hands. The only thing that's gonna be different is then I don't need the nested for loop here, because then I don't need to loop over the players. I can just loop over the actions. But I still think I'm gonna need another loop anyway to loop over, but then it's a lot more efficient because I'm only looping once instead of looping each time for each player for each round. I think it's more efficient. Just trying to think if there's a way to make it more efficient. But I think I can't avoid the extra loop because I need to get all the actions for each round anyway. This is an object and then creates the round for the object and then creates the list, which is gonna contain all the actions for all the players. And then I take that and append the action. Yeah, I think I'm gonna run this and I'm gonna get something into it, and then I'll see if I can improve even more. But I'm probably gonna build the stuff after. Like I'm gonna leave it like this, then try to build this thing to get the sequence of actions, and then I'll think about whether or not I can improve further on the way that it is structured. Because this transforming the batch sequence into a line is gonna be very hard, I think. Yeah, and I might stop here. I'm not really sure, because the thing is I'm gonna have to spend a lot of time just thinking without doing anything to think about how I'm gonna translate the line into translate the sequence of actions into a line. So I think it might be better to do that off stream, so I can just like spend time thinking. So what I might do is just try to improve this part first on stream, and then I'll think about these parts off stream, and then the next time that I'm streaming I explain what I did or what I came up with to translate. So I'm gonna run, and we're gonna run this, and I'm gonna grab something to eat. So I'll be right back. think I'm just gonna read the Ethereum book while I eat. I just realized that it's probably better to, the best thing to do is use a tree data structure to translate the actions. The actions are a linked list. I can think about it as a linked list. So it goes from one to whatever action it is, and then the boundaries that transform the linked list into the tree is the rounds. And then each node can be either a fold, call, or raise. So it's a decision tree. But I have to think about how I'm gonna do that. I think I'm gonna use scattered draw to make it more clear in my mind, because it's kind of difficult to think about all the possible situations and how to structure the tree nodes so that each action, so I can translate the sequence of actions into the batting line each time. Because then I'm gonna use that tree to later on to populate the simulation here with the bat sizes. So I can, that's another algorithm that I'm gonna use. I'm gonna have to build, like traverse the tree and then put the bat sizes depending on this thing here, which should be really interesting to do. It's the first time that I'm gonna put apply some of these data structures in an actual problem. So it was really cool. I think I'm not really sure what I can watch here, or I think maybe I'm just listening to the book while I eat. Just listen to the transactions.
Unwatch. Stop ignoring. Watch. 583. Notifications. Participating in net mentions. Only receive notifications from this repository when participating or at mention. All activity. Notified of all notifications on this repository. Ignore. Never be notified. Custom. Select events you want to be notified of in addition to participating in net mention. Get push notifications on iOS or Android. Custom. Custom. Select events you want to be notified of in addition to participating in net mention. Issues. Pull requests. Releases. Discussions. Discussions are not enabled for this repository. Security alerts. Apply. Cancel. Fork. 4.3k. Fork your own transactions. Transactions are signed messages originated by an externally owned account, EOA, transmitted by the Ethereum network, and recorded on the Ethereum blockchain. This basic definition conceals a lot of surprising and fascinating details. Another way to look at transactions is that they are the only things that can trigger a change of state, or cause a contract to execute in the EV. Ethereum is a global singleton state machine, and transactions are what make that state machine tick, changing its state. Contracts don't run on their own. Ethereum doesn't run autonomously. Everything starts with a transaction. In this chapter, we will dissect transactions, show how they work, and examine the detail. Note that much of this chapter is addressed to those who are interested in managing their own transactions at a low level, perhaps because they are writing a wallet app. You don't have to worry about this if you are happy using existing wallet applications, although you may find the details interesting. The structure of a transaction. First, let's take a look at the basic structure of a transaction, as it is serialized and transmitted on the Ethereum network. Each client and application that receives a serialized transaction will store it in memory using its own internal data structure, perhaps embellished with metadata that doesn't exist in the network serialized transaction itself. The network serialization is the only standard form of a transaction. A transaction is a serialized binary message that contains the following data. Nonce, a sequence number, issued by the originating EOA, used to prevent message replay. Gas price. The amount of ether, in way, that the originator is willing to pay for each unit of gas. Gas limit. The maximum amount of gas the originator is willing to buy for this transaction. Recipient. The destination Ethereum address. Value. The amount of ether, in way, to send to the destination. Data. The variable length binary data payload. VRS. The three components of an hexadecimal signature of the originating EOA. The transaction message's structure is serialized using the recursive length prefix, RLP, encoding scheme, which was created specifically for simple, byte-perfect data serialization in Ethereum. All numbers in Ethereum are encoded as big-endian integers, of lengths that are multiples of 8 bits. Note that the field labels, to, gas limit, etc., are shown here for clarity, but are not part of the transaction serialized data, which contains the field values RLP encode. In general, RLP does not contain any field delimiters or labels. RLP's length prefix is used to identify the length of each field. Anything beyond the defined length belongs to the next field in the struct. While this is the actual transaction structure transmitted, most internal representations and user interface visualizations embellish this with additional information, derived from the transaction or from the blockchain. For example, you may notice there is no from data in the address identifying the originator EOA. That is because the EOA's public key can be derived from the VRS components of the EXA signature. The address can, in turn, be derived from the public key. When you see a transaction showing a from field, that was added by the software used to visualize the transaction. Other metadata frequently added to the transaction by client software includes the block number, once it is mined and included in the blockchain, and a transaction ID, calculated hash. Again, this data is derived from the transaction, and does not form part of the transaction message itself. The transaction nonce. The nonce is one of the most important and least understood components of a transaction. The definition in the yellow paper, see references, reads. Nonce, a scalar value equal to the number of transactions sent from this address or, in the case of accounts with associated code, the number of contract creations made by this account. Strictly speaking, the nonce is an attribute of the originating address, that is, it only has meaning in the context of the sending address. However, the nonce is not stored explicitly as part of an account state on the blockchain. Instead, it is calculated dynamically, by counting the number of confirmed transactions that have originated from an address. There are two scenarios where the existence of a transaction counting nonce is important, the usability feature of transactions being included in the order of creation, and the vital feature of transaction duplication protect. Let's look at an example scenario for each of these. Imagine you wish to make two transactions. You have an important payment to make of 6 ether, and also another payment of 8 ether. You sign and broadcast the 6 ether transaction first, because it is the more important one, and then you sign and broadcast the second, 8 ether transaction. Sadly, you have overlooked the fact that your account contains only 10 ether, so the network can't accept both transactions, one of them will fail. Because you sent the more important 6 ether one first, you understandably expect that one to go through and the 8 ether one to be rejected. However, in a decentralized system like Ethereum, nodes may receive the transactions in either order. There is no guarantee that a particular node will have one transaction propagated to it before the other. As such, it will almost certainly be the case that some nodes receive the 6 ether transaction first and others receive the 8 ether transaction first. Without the nonce, it would be random as to which one gets accepted and which reject. However, with the nonce included, the first transaction you sent will have a nonce of, let's say, 3, while the 8 ether transaction has the next nonce value, i.e., 4. So, that transaction will be ignored until the transactions with nonces from 0 to 3 have been processed, even if it is received first. Phew. Now imagine you have an account with 100 ether. Fantastic. You find someone online who will accept payment in ether for a MacGuffin widget that you really want to buy. You send them 2 ether and they send you the MacGuffin widget. Lovely. To make the 2 ether payment, you signed a transaction sending 2 ether from your account to their account, and then broadcast.
So in this part 7, we are going to now talk about breadth first search. Now, breadth first search is really very important because it's going to help us print out all the nodes of this tree in a breadth first manner. So basically, it is also called level order traversal. So basically, we are going to be taking this level, and just like that. So if you are going to do a breadth first search, intuitively, you are going to go from G, and we go to C and I, B, E, H, J, B, E, H, J, and ADFK. So there is a breadth first traversal of this tree. Now, one question you may ask is there a relationship between this breadth first traversal and the 3 different traversals we talked about, in order, post order, and pre-order? Well, we're going to talk about this a little later. Let's just complete this algorithm for breadth first search. So the algorithm for a breadth first search for a binary tree, and of course for any tree and even graphs, uses a queue and a list of nodes. So what it simply means, if you visit a node, then visit its children. If you visit a node, visit its children in the same manner, all right, or in the same level. So this is how it plays out. So the first step, we are going to take the root of the node and push it onto the queue. So we are going to take the root of the node and push it onto the queue. So here we are going to have G, and we also add it to visited node G, all right? The next thing we are going to now be doing is we are going to iterate this queue, and once there is an item on this queue, we are going to add the children of that item to the queue. So once we have G here, the next thing we are going to check is the children of G, right? So the children for G is C and I. So I'm going to say C and I. And once that happens, I'm also going to pop G from the queue. Or maybe I can just erase it. Yeah. So let's just cancel it out. All right. So the next thing we are going to do is to move one step in the queue. C, we have the children are B and E. So I'm going to just add them to the queue B and E. We add them to the queue B and E. And then each time you add the children of a node, or the left and right children of a node, just pop it out from the node. So I'm going from the queue. So I'm going to just say C. And once you are removing anything from the queue, it's guaranteed that it's going to remove from the front of the queue or from the back of the queue the item that was first added. So we have E here. So we are going to now move to I. So you can see I here. I has 2 children, H and J. So I'm going to add them to the queue, H and J, and pop I from the queue and put it into the list of visited nodes I. All right, so we now move to the next part, which is B. B is the next one. It has an item, node A. So we are going to add A to the queue, and we are going to pop B from the queue and add it to the visited nodes. All right. Okay, so we now have E. E has 2 children, and the children are D and F. So I'm going to add them to the queue, D and F. Okay. And remember, if you're adding to the queue, of course, you can add something that you already added before. All right, so we now go to E. It has D and F. We've added D and F to the queue, so we are going to pop E from the queue onto the list of visited nodes. So I'd like you to pause the video at this time and try to complete this yourself. But for just tutorial purposes, I'm going to just complete it. So we have H. H has no children, so I'm going to just pop it from the queue and put it in the visited nodes. We have the next one is J. J has a child, K. So I'm going to add K to the queue and pop J from the queue and add it to the list of visited nodes. The next one is A. A is this one. It has no children, so I'm going to pop it and put it right here. The next one is D. D has no children. Pop and put it right here. F is the next one. F has no children. Pop it from the queue, or dequeue it from the queue and put it right here. F. So I actually use pop. It's actually the queue. And finally, we have K. K has no children. Pop from the queue and put it right here. So at this time, the queue is now empty, and we have our breadth first search, right? So this is basically how the algorithm goes. I hope it's clear. And in the next part, we are now going to use exactly these two data structures, queue and a list, to implement it in Python. So let's see in the next part. Meanwhile, please subscribe to my channel if this has been informative for you. Also, leave me a comment if you have any questions whatsoever.
Hello people from the future, welcome to Normalized Nerd. In this video, I'm gonna show you how you can code your very own decision tree classifier completely from scratch. Yes, I won't be using any library that has the predefined code for implementing decision trees. I will be using only NumPy and Pandas. If you are new here, then please subscribe to my channel and hit the bell icon, because in the next video, I will explain how decision tree regression works in great detail. So let's get started. First of all, I would highly recommend you to watch my previous video where I have explained the concept and math behind decision tree classification. Because if you don't know the concept behind something, how can you code that? So please watch the previous video and then continue with this one. The video link will be appearing in the cards right now. Okay, let's start the coding. So as you can see, first of all, we have to import the tools. And by tools, I mean two libraries, NumPy and Pandas. After that, we need to gather the data, because to train our model and to test it, we need some data. Well, the data that I'm using here is a very common data. It's a dataset about iris flowers. You can just Google iris dataset and just download the CSV file. Well, I have downloaded it previously and kept it in the same directory as of this Jupyter notebook so that I can access it with Pandas. There are three types of iris flowers in this dataset. I don't remember the names, but you can see them in the type column of the Pandas data frame. The type column contains three values, 0, 1, and 2 for the three respective classes. We have got four features here: sepal length, sepal width, petal length, and petal width. Once we have the dataset, now we can work on the model. To make our life a lot easier, I have used here object-oriented programming. Trust me, to write this kind of machine learning algorithms, if you don't use object-oriented programming, then it will be a nightmare. So if you haven't learned object-oriented programming in Python, then it's a great time to start. Okay, so I have used two classes here. The first one is node class and the second one is the tree class. Well, as the name suggests, the node class will describe the nodes of our decision tree. And as you can see, node is a very small class with just the constructor in it. We will define several attributes in the node class. Those are feature index, threshold, left, right, information gain, and value. Well, if you have remembered my last video, there I mentioned that a decision tree contains two kinds of nodes, decision nodes and leaf nodes. The decision node contains a condition, and the condition is defined by the feature index and the threshold value for that particular feature. The left and right are for accessing the left child and right child respectively. You can imagine left and right as the edges of the tree, because it will help us to move from parent node to its child nodes. And the last one is information gain. Well, this variable stores the information gained by the split denoted by this particular decision node. And for the leaf node, we don't need any of the previous variables. We only need the value. And what is value? Well, it is just the majority class of the leaf node. It will help us to determine the class of a new data point if the data point ends up in this particular leaf node. Okay, now comes the tree class. And in this class, I have implemented the whole algorithm. So this class will contain the tree building method, entropy calculation method, splitting method, prediction method, etc. First, obviously we need to define a constructor. In the constructor, I have defined 3 attributes. And these attributes will be used by different functions that I will define inside the class. So the first attribute is root. And we will need this root to traverse through the tree. And then the 2 attributes are just the stopping conditions, minimum sample split and the max depth. So if in a particular node the number of samples becomes less than the minimum samples, then we won't split that node any further. We will treat that node as a leaf node. And if the depth of the tree reaches the maximum depth, then also we won't split the nodes further. Okay, then comes the most important function of this class, build tree function. It is a recursive function to build the binary tree using recursion. So first of all, it is just splitting the features and targets into 2 separate variables, x and y. It will make our work a bit easier. Then it's just extracting the number of samples and the number of features, which we can easily get by using the np.shape function. In the first if statement, I am checking if the number of samples is greater than or equal to minimum samples and the current depth is less than or equal to maximum depth. If these 2 conditions are not met, we can't split the tree further. Then we are using the getBestSplit function to get the best split. At this moment, please don't worry about the getBestSplit function because I will explain the working of that function in a moment. So after that we have got the best split, we will check if the information gain corresponding to this split is greater than 0. Why? Because information gain equal to 0 means we are splitting a node which is already pure. That is, the node consists of only one type of class. And that doesn't make any sense. After that, we are gonna create the left subtree and the right subtree respectively. Please notice that here is the recursion because we are calling the buildTree function inside buildTree function. So first it will create all the left subtrees, and then once it has reached the leaf node, it will create the right subtrees. The important thing to focus on here is we have to increase the current depth variable here. Okay, after the trees are done, we need to return a node, and this node will be a decision node. And as it is a decision node, we have to pass feature index, threshold, the left subtree and right subtree connectors, and the information gain. By the way, as you can clearly notice, BestSplit is actually a dictionary that is returned by the getBestSplit function. Okay, after these things are done, we need to compute the leaf node. So to calculate the leaf value, I have defined a function called calculateLeafValue, which I will explain later. And at last, we need to return the leaf node. And as it is a leaf node, we only need to pass one attribute, that is the value. Okay, so this was the buildTree function. Now comes the second most important function, getBestSplit function. So as you have already seen in the buildTree function, getBestSplit function returns a dictionary. So at first I have just defined an empty dictionary called BestSplit, and I have initialized a maximum information gain as -infinity because we want to maximize the information gain. And to find that, we have to use a number that is less than any other number. Now, first we are gonna loop through all the features. And inside this loop, we have to traverse through all the possible threshold values. Now, the features are real numbers, and there exists an infinite number of real numbers between any two real numbers. So it doesn't make sense to iterate through every possible real number. Instead, what we do, we just traverse through every possible value of a feature that we have encountered in our dataset. And np.unique function just returns the unique values of a particular feature so that we can traverse through all the possible values of that feature. Okay, so now we are inside the second loop. Here, first of all, we split the dataset based on the current feature index and the current threshold. Now again, don't worry about the split function here. I will explain it later. Okay, so at this stage, we have got the left dataset and right dataset. Now we need to ensure that these are not empty. So once we know that we have something to work with, then I am just extracting the target values that is denoted by Y here. So after that, we need to compute the information gain. And to compute that, I have used here a function called information gain. And don't worry about the implementation now, I will explain that. And you can see that I have used Gini index here for calculating the information gain. And I will explain that also. Okay, so once we have got the current information gain, we need to check if this current information gain is greater than the max information gain. If it is greater than that, then we need to update our BestSplit. And here you can see all the keys in the BestSplit dictionary. Once the nested loops have completed their executions, we can just return the BestSplit. So here's the split function that I used in the previous function. This function takes the dataset and the feature index and threshold value and splits it into two parts. The first part will go to the left child and the second part will go to the right child. And the way to do this is very simple. I have just used the list comprehensions. As you can recall from the last video, in the left child, we will send those data points that met our threshold condition. So you can see here, I am passing all those rows for which the feature value is less than or equal to the threshold value. And in the right child, I am passing those rows for which the particular feature value is greater than the threshold. Now the function that calculates information gain. This information gain function just subtracts the combined information of the child nodes from the parent node. And you can see I have used here some weights. Well, as you already know, weights are nothing but the relative sizes of the child nodes with respect to the parent node. In the last video, I have mentioned only the entropy as the measure of information. But here you can see two different types of function to measure the information contained in a system. The first one is entropy and the second one is Gini. So let me tell you what Gini index really is. Recall that in the last video I have shown you the formula for entropy and how it was helping us to calculate the information contained in a state. Well, the Gini index does exactly the same, but here the formula is a little different. So you can see we have removed the logarithm. So now it's just pi square and we are subtracting the whole sum from 1. By removing the logarithm, we have actually done a favor to us. Can you guess what it is? Yes, it saves us some computation time because logarithm is a little hard to find than just computing the square of a quantity. Okay, so by using this formula, let's calculate the Gini index for all the 5 states here. Once we have got the Gini scores for all these states, we can easily find the information gain by using the previous formula. And by doing this, we can clearly see that the second split is a better option for us. And the entropy also agrees that the second split is a better one. Back to coding. The following two functions just calculate the entropy and Gini index for a given array of target variables. You can cross-check these two functions with the actual formula to convince yourself that they are doing exactly what we need. After that comes a very little function that calculates the value of the leaf node. Well, as you know, the value of a leaf node is just the majority class present in that particular node. So we just need to find the most occurring element in Y. After that, I have written a custom function called printTree. This will just help us to visualize our decision tree. Well, there is really Really not much to explain here. This is just a recursive function that prints the tree by following the pre-order traversal. After that comes the fit function. Well, if you have ever done scikit-learn, then you can just see that I am trying to mimic their fit function here. So inside the function, I am first concatenating the x and y to create our dataset, and then I am just calling the build tree function. And see here that the root node will be returned by the build tree function, and I will store that into our self.root. After that, we have a predict function. Well, this function will just take a new dataset. By dataset, I mean the matrix of features, and it will return the corresponding predictions. You can see that I have used here a function called makePrediction, which is defined just below it. You can see that the makePredict function takes a node as its parameter, and initially we are just passing the root node. Coming to the function, if the node.value is not none, that is, if the node is a leaf node, then it just returns the value. And if it is not a leaf node, then we extract the feature value of our new data point at the given feature index. Then we check if the feature value is less than or equal to the threshold. If it's true, then we recur through the left subtree, else we recur through the right subtree. Okay, so that was it. We have successfully coded our decision tree. Now is the time to train it and test it. So naturally, first we need to split our dataset into training set and test set. And for that purpose, I have just used the train test split function. So here I have created an object of the decision tree classifier class called classifier. And I have mentioned minimum sample splits as 3 and maximum depth as 3. After that, we call the classifier.fit function, and we need to pass the xtrain and ytrain, and then I'm just printing the tree. So here's the printed tree. So this is the tree that our model has built. Okay, so finally we need to see how accurate our model really is. And for that purpose, I'm gonna use the accuracy score function from sklearn.matrix module. And just look at the result. It's over 93% accurate on test data. And remember, we have coded it from scratch. I haven't used any other module. For me at least, it's so satisfying to see a model performing so well, especially when the model is coded by us from scratch. So that was all for this video, guys. I hope you really enjoyed the code, and you can find this whole notebook in the video description. And don't forget that in the next video, I'm going to explain regression using decision tree. Yes, there will be a lot of visuals too. So subscribe the channel, share this video, and thanks for watching.
Hi thinkers, welcome to the Data Structures in Python course on thinkexacademy.com. In this series, we have already covered introduction to graph data structure and its representation using adjacency list. Now we are going to cover traversal in a graph data structure. The first technique to do traversal or search in a graph data structure is the best, which is the breadth first search. And breadth first search is very important. It has a lot of applications, and in a lot of interviews, there are a lot of questions that come from this particular algorithm. So we will write the algorithm in Python. So first of all, we have a given graph data structure here, which is has these vertices, and this is how it is connected. So we have 0, 1, 2, 3, and 4. So the first thing I'm going to do is in this program, I'm going to actually, and here I will write the main function using name equals to. Here I will first create a graph representation of the corresponding graph that I've drawn here. The first way is to use the matrix, the second is to use the adjacency list, but here we have an interesting option, which is the third option, which is to create a dictionary, right? So here we are actually trying to create a dictionary here. So I will just write that we are going to create a dictionary to represent this graph. So in dictionary, we have keys, and separated by colon, we have values. So it's something looks like this, right? So basically we are going to write the keys as the vertices. So 0 is a vertex, and then we have 1 as the vertex, and then we have 2 as the vertex, and 3, and then 4. And now what I'm going to do here is, in the values, I'm going to provide an array. In this array, we will actually put all the elements that are directly connected to this node. So if we consider 0, 1 is connected, 2 is connected, and 3 is connected to it. In case of 1, we have a 0 connected to it, and then we have 2 connected to it. And now let's consider node number 2. It has 0 connected to it and 1 connected to it. And the final one is 3. And here 3 is connected to only 0. And the last one is 4, it is connected to 2. So here we have a representation of this graph, and we will leave some indentation here. So now what I will do is I will make a call to a BFS function here, and here I will supply it with two values, graph, which is this dictionary, and also the node from where I wish to start the traversal, right? So 0 is the node from where I want to do the traversal. So let's understand what exactly is breadth first search now before implementing this function, and let's see what is the approach in the algorithm. So here we are going to start from this root node. So I'm going to write here that this is the starting position. The basic idea of breadth first search is to traverse, or is to display all the adjacent nodes to it, right? So if we are going to start the traversal from 0, the BFS algorithm is going to move the traversal in such a way. So we will first print 0. 1 is directly connected to 0, you can see that. 2 is also directly connected to it, and 3 is also directly connected to it. So first we will display 1, then we will display 2. Now when we reach 2, we can see that 4 is connected to 2, but we are not going to display it because this is the main rule of breadth first search, that we are going to first go to the breadth, and then only we are going to increase the levels. The next one we will have to display 3, and now we are going to display the values of the neighbors of these, which is 1, 2, and 3. So 1 has a neighbor 0 and 2. Both are already being traversed. So once we have done traversal on a node, we are not going to visit it again. Similarly with 3 also, 0 is already visited, but 4 is not visited. So now I will insert 4 here, right? So it is known as breadth first search because if you consider a tree, a data structure like tree, and we apply the same rule, which is to display all the adjacent nodes. So if I will try from the root node, we have these two adjacent nodes. So basically we are actually trying to traverse level by level. So that's why it is known as breadth by breadth, right? So this is a breadth first. In depth first, we are going to explore in the depth, right? So if I go from this node to this node, I can ignore these nodes. I will first explore this node to the whole extent, right? So that's how the DFS and BFS works, right? So now let's see how we can implement this in Python. So first thing is we are going to create a visited array, right? We can use the set function to create such type of an array, and initially this array is empty. This visited array is going to be the final output where we will display all these, we will display all the nodes which we have traversed. The second thing is we are going to use a queue data structure. Queues are basically used to perform BFS algorithm because it is actually a very feasible data structure in this type of scenario. So initially the queue will hold only one element, which is 0, which is the root element, right? So we will first add 0 to the queue. So first of all, let's implement this part in the in our Python file. So the first thing I'm going to do here is I'm going to define a function BFS. It will take the graph and it will take the root element, and in the next line I'm just going to write I'm going to create a visited array using set function, and then I'm going to simply create a queue data structure, right? Now here we can actually create a queue using list in Python. We can create an empty queue, and we want the first element, root element, should be there. So we can do it something like this. This is not an ideal way. We will use the collections library because when we want to perform frequent NQ and DQ operation inside of a queue,
I'm going to put another hour here, and then I'll take another break. I was thinking about it as I was eating, but I still can't figure out the problem, how to solve the problem, because the challenge here is to translate the actions into the tree. So to figure out how to determine the if-else statement so that I can place the logic to connect one node to the other. So I was thinking about it, about making the player tree be a decision tree of bet, raise, call, or fold for all of the players. And then each action is a node on the tree, then the value would be one of these four here. And then the children, I'm not really sure, like, I think it would be the other actions, maybe? The other actions. So like the greater the node, so for example, action number 1 has all of the other actions as neighbors, as children. But action number 2 only has the actions that are lower than, greater than 2 as children. So yeah, I think that way works. So, but the thing is that's the thing. Because then that way it doesn't encapsulate the logic, I think, for one node to the other. I can make the conditions based on value and then create the children like that. But I think the main idea, I'm not really sure if this is the best as well, but you create a tree for every player. So for each player in the hand, I create a tree structure of decisions, and then I use the list of actions, which are nodes. It's kind of like a linked list of actions. And I create the player tree based on that list. But then the question is, how do I translate the actions there? Because I still have the problem of figuring out whether an action is a bet, a raise, a call, or a fold. So this is the stuff that I was trying to figure out how to make it better using the tree data structure. So it's easier to determine what is a bet. Because obviously I'm gonna have to do it based on the rounds as well, I think. And the question is, how do you define what is each thing? And then from that point, I'm not even sure if that is necessary to have the tree anymore, if I can figure out how to determine what's each thing. I think it would be good. Yeah, I was thinking about it as well, because the tree is going to contain all the possible actions. So creating the tree containing all the possible actions that exist for the level, for the hand. But that might be inefficient as well. So for example, let's say there are 7 actions for the current hand. So I create a tree for all possible decisions. Not all possible decisions, because obviously it would be too many. Actually not all possible decisions, because it's just going to be 4 times. So because for each action, the player can have 4 possible decisions. So the whole space of decisions of the player would be 4 times the amount of actions that exist on each hand. And then I would do that for each player. And then I select the actions that were taken. Because the thing on the simulation is going to do that anyway. So I think that's how the simulation is done. And then I just replace, the only thing then is the bet sizes, I think. Let me think more about this. The problem is there's a position as well. And the position is what makes it difficult, I think, because otherwise I could create just one tree structure for all of the players and just have all the possible actions on the tree structure. So accept the number of actions here, for example, and then I can just create the nodes based on the amount of actions. And then each possible action would have four different nodes connected to each other, or connected to one of the other nodes, and then those 4 nodes would have 4 nodes, and so on. So 7 levels actually. The depth of the tree would be the amount of actions, and then each level would have, it would scale exponentially, maybe. Yeah, because the first one has 4, then the second has 4 times 4. It grows exponentially, so it's not that good, I think. And then I could create something that traverses the tree and gets the specific line of the hand. And this is stuff to think about. Let's see something. I think that ChatGPT answers is not going to be very good because they don't know how to structure the question really well. It's going to be too generic. I need to clarify more what I'm trying to do there. So I have the list of actions. It's so annoying. I want to increase the size of this thing here. I'm also getting a bunch of ideas that I can do once I have the simulations. And so I have a list of actions like this. And then the question is how to translate this stuff into here. How does it feel like it's going down? So what is the best way to do this? And the way that I'm thinking, each one of these nodes would be raise or fold. Folds. Oh. Bends. Raise. The problem is And then for each one of these, except fold wouldn't have children. But then for each one of these would have 4, for the bats, would have 4 more levels. Right here. Then this is the player. Doesn't need to be perfect. Then the problem here is that like it's not gonna be linear, because here can be an action of player 1, then player 2, then player 4, then player 1 again. What do you think? The problem is that there are several different questions, like if it is even better to do 1 3 of the player and then translate the actions here, or to do another 3 that has another relationship. I think that the 3 for the player would be good, because then like you can get the lines. It's easier to get the lines once you translate, I think, because then the lines are only gonna be the path. You can create a function that gets the path based on the actions. To pass a list of actions to the functions, and then it traverses the tree to figure out what's the but let me. Because this way I think it doesn't work really well, because the actions are for all the players, so that's the problem. Or maybe not, because that's what I'm trying to do. So what I have to create an algorithm to get a list of actions and then get the paths. So I build like a template, which is a decision tree for all possible decisions on that hand based on the amount of actions that it has. And obviously it's going to go overboard, but that's also another thing, that it might be inefficient. Because if there are only 7 actions, you have to create an exponentially bigger tree to handle all possibilities. And it's obviously not going to be the case, because otherwise there would be more actions, because the players can't take that amount. So it's probably not the best way, I think. The other information that I have is the rounds for each thing. So each action, so that's another possibility, is to create the rounds as the nodes, and then the actions as the children of the, or create the tree of rounds and actions. But the 3 things need to be involved: the round, actions, and players. And I think that a 3D data structure is probably the best. So I have to think about how to integrate the 3 different things into either 1 tree or 2 different trees in the way that's going to be the best. And here I think it is correct the way that it is here. It's really difficult to think about though.
So high. Do you think of my heart? Do you have the time? Do you think of my
I guess I can filter the actions to get the players, like only actions that are relevant to the player. But it's still the same issue. Like the core of the issue is figuring out how to translate the line into translate the sequence of actions into the line, the betting line for each player. I think that's the key. So I have a line, for example, bet, call, check, bet. So I need to translate this into this for each player, I think. That's the algorithm that I need to think about. And what is the best data structure to accomplish that? Because the thing is that the actions are from all the players, so the sequence gets messed up because you can't infer from the sequence the line for each player.
Do you think of my heart? Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a love
And just doing this stuff while I think about it. It's very hard to... There's nothing I can do. I need time to think about what would be a good solution. I'm sure we're gonna find something. Maybe it's better to do like this.
You're so high. Do you think of my heart? Do you have the time? Do you think of my heart? Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a love right now. Hey, I need a love right now. I need a
So it looks like it's messed up here. Players. It ends here. It's here.
in another world. If you lose control,
Then I have the actions.
if you lose control,
0.
if you lose control, in another world. If you lose control.
I think it's just missing the last one, maybe. Or this one, because of is the end of the thing. Yeah, I think that now is correct. Yeah, there we go. It's kind of confusing like this. They should have done like this.
Now that's two opposing thoughts, and yet both of them are true. How can you experience everything you
Yeah, but now
choose
I think this is a lot easier to get the actions, and I think this is correct. So,
See, it's the
and
question
the players here, the cards, the position,
otherwise you couldn't differentiate between the two.
and then the actions.
Awareness.
And then I just have to loop once through the
You
actions.
think you hurt me, but I
Or
promise I
to...
was left.
Actually, I need to loop for each round once, but then it's just one time, instead of doing for all the players. I think this is much better.
I am the journey that I'm getting to.
And the actions are in sequence here, which is also a lot easier to understand. So now just the challenge is how do I translate this into... How do I translate this line of actions into the lines for each player. And I think I do it with the decision tree. The difficult thing is that like I can only create the nodes for one player based on the other actions. So I can't store the... I can't create the node for the player and then only create the tree based on the player's action, because it's gonna depend on the other actions. So the only way that I can think about it to classify what would be the decision is by having the other actions from other players.
Destination. My destiny
So the
is
whole
not
decision
mine.
thing has to come from the sequence.
So I travel back in time. I have everything I want because my imagination.
So I think I need to think about the heuristics first.
It's not enough for me, 'cause I am
Now, obviously,
I could see it.
the 0 I think is the easiest one when some 0.
I could be it.
It's either a check
Identity is intertwined.
or...
The moon
Yeah, it's a check always, because if he folds, it's not gonna show the action. That's difficult. I think I might stop here, to be honest, and just think about this offstring. It might take a long time for me to think about something. Zero. Maybe I'll spend the rest of the hour here and then I'll stop. There's 1, 2, 3. So I also have to use the sum, obviously, to get the information.
It's not the human race. It's just the human race. There's nothing left to chase. We do not run this place. But both medicine and poison's an acquired taste. So I started taking selfies of somebody else's face.
Also looked like this was a 3-bet, I think. Yeah, and then I folded. So posted the blinds, then 0, 3. So I need to think about... Yeah, I can't really... If it was always the same, then I think it would be easier. But because the amount of actions here on round 0 can vary, then it becomes more challenging as well. So maybe I can use one tree to determine the rounds, like flop, turn, and river. Actually, I was gonna say that it was kind of dumb to put numbers instead of putting the names. But obviously it doesn't matter that much. It's just a nuance. But it would be better actually if it was numbers there. So I might do that off stream. To change the thing. Change this to should be the name stuff based on the number. It doesn't matter that much. So what can I do here? So each round can be a node of a tree. In which round it changes you can change the line of the thing. The problem is that the round 0 doesn't have anything to do with the line itself. But because there can be more actions here, I have to think about it, I think. Or maybe I can just count the number of actions here on the round 0. I can do the length there, I think. And now I do it like this, and then I'll raise this stuff. And this would be this thing here. Actions is a dictionary, so it wouldn't be a loop. I think I have to do 4 loops for each round. There's no way to avoid that. I can get the length actually for the thing. So if length this is greater than 2, then I do something. And then for the other ones I do a for loop. So here I'm just checking to see if there are more people posting blind, so then I can keep track of the other actions in a different way. Now let me think. But I'm not sure if it matters anyway, because like what matters is the order of the number of the actions. Because I know pre-flop is gonna start with early position. No, this is also looks like this is wrong. Fuck. I'm gonna have to see this again. It's saying player 5 is early position, but here is saying that player 3. Oh, but it might be right because this might not contain the. Oh, but that doesn't make sense. At player 5, so it's probably wrong here.
Je crois que je poursuis un rêve impossible.
Fuck.
Je pense que ça marchera pas, mais
And I have to think about this now.
je nous revois, je revois tes yeux, je revois ta bouche, je revois tes cheveux, ton visage.
Oh, maybe not. Oh no, yeah, it's definitely wrong. Because either way,
Tu me
Player
revois
5 wouldn't be the
fermer les
bottom
yeux quand tu
if this is the
rêves.
third, should say here.
C'est un rêve impossible.
Here.
Tu m'avais dans la
No,
paume de
player
ta
3
main,
is the
tout ce que
bottom.
t'avais à faire, c'est de me dire de rester.
So where's player 3
Mais
here?
t'es parti. Et t'es
It's the
revenu.
first to talk.
Et puis t'es reparti. Et puis t'es revenu. Encore et encore.
On round
Et à chaque
1,
fois, c'est la même
it
chose.
isn't flop. Really. Even if it is flop, it doesn't make sense. Yeah, so this is not correct.
Tout ce que t'avais à faire, c'est de me dire de rester. Et je serais restée pour toujours. Toujours avec toi. Alors pourquoi t'es parti? Pourquoi tu m'as laissé? Ça va nous échapper entre les doigts et un jour ou l'autre de toute façon, tout ça, ça va s'arrêter.
Let's see. 0, pre-flop. No, 1 is definitely pre-flop. Because I know that it goes up to 4. 4 rounds. So 4 is river, 3 is turn, choose flop, 1 is pre-flop. And 0 is blinds. But this is incorrect. This here is player 3 and action 3. And player 3 is supposed to be the bottom. Let's see, 1, 2, 5. But there's only 5 on this one, so I'm probably messing it up on the calculation there. To increase the number when there are less than 6 players. 5. Yeah, because I think that it would be correct if player 3 was the small blind, because the small blind is the first. Oh, but actually this is pre-flop. So player 3 would have to be early position. So it starts with the small blind. Number 1 small blind. And so this is the problem. I messed it up. But maybe the issue is that this doesn't retain the information of the order of the position here. Maybe just as number 2 is the action. Yeah, but it looks like it is retaining. No, here because number 5 doesn't retain the information. So I'm gonna have to redo this thing here. So I'm gonna have to do the more complicated thing, which is to get the information of the position from the rounds and not from this thing here. I think what I can do is put this on a function, this part here, and then I just call that. Oh, the thing is that it's gonna be different because like the whole logic to get it is different. And so I would have to get it, you get the position based on the action here, action number. So I think I need to put it here, and then I do the same logic that I did there, but I do it here, and do this logic here, and then I do it based on the action number. But it has to be based on the round as well, not only this but the round. But I'm still thinking, I'm still with the other stuff in my mind, this stuff here. There's so much stuff to think about. I don't know which thing that I focus now on first. Because I wanna figure this out as well, because the actions is the hardest part. This one is just annoying that I'm gonna have to redo it, but it is not gonna be difficult. I just do it inside of here, and then I'm gonna put extra conditions here, probably after this action. Like I can get I'm gonna create a variable here, action number, then make it equal to that, and then I use this variable. And maybe I should do that now, and then I focus on the other stuff there. Because I'm gonna have to think about the other stuff for a long time. So I pass this thing here to the other. I put if name equals. Yeah, I think or maybe this has to be outside of here. Or maybe not. No, I think it has to be outside because it doesn't matter if it is, because I'm already using the player map to... I forgot what I did here. No. Yeah, but I think I can put it like this here, and then it's gonna be the same thing, and then I just translate the other stuff here. But the difference is that I need to put based on round. So I can use the current round. That's why I think it's better to do a function, I think. So if current round... Yeah, because that's what makes it more difficult, is that the actions are gonna change based on the... They can vary depending on the amount of rounds. I forgot how I did this on the other time. Because it's not only the amount of players, but the how much the actions can vary. But I think I can use around 1 always to get the information. The first to act on round 1, which is pre-flop, is gonna be early position, and then I just subtract. I think I can do it like that. And then I do the same logic. I have current rounds. Oh, actually, so if current round is 1, then I do this stuff here. Let's see, think about another name here. And then remove this stuff. I think this probably will solve it. 'Cause now I'm doing the same thing that I was doing before, but I'm doing for the round 1, and now I have to change the conditions here. I think the conditions are the same. It just changes because of the... let me think about the map, the whole map thing. Because the map was done based on the player counts. Each time there's a player, I add and put the count and then increase the count. So I think that the map doesn't change. The map is gonna be... the keys are gonna be the names of the players, and the player count is gonna be starting from 1, the value. Well, let me think. Yeah, the problem is I can't use the player. Because it doesn't matter the position the sequence that they're added. What matters is the actions. So I don't think I need the player map anymore. You just get based on the action. Oh no, actually the player counted does make sense, but the player map doesn't. Because what I want is the... actually, let me see. If player spread bigger than 0, then it means that there are less than 6 players. In this case, I do something. I'm gonna decrease. Let me think. Because the issue is I need to do it kind of like a loop, where the first time, like, I make the... I'm also gonna change these conditions. First time I make the player position equal to EP. But the problem is, how do I know what is the first time? Like, I have to get based on the actual number, but then the actual number can vary each time. That's the issue. That's why it's hard. I think maybe this is why I need to run some logic on when it's round 0. This line here. But I don't wanna like make it more complicated. Like create another flag variable and then use the flag variable to count the amount of actions on the round 0 and then use that. It would be much better if I could just count from round 1. So I guess I can decrease the counts. And then I make, if different than 0, then I go over this stuff. Yeah, I do the same way, so, but here, instead of doing this, I do based on player counts. And then I decrease the player counts each time. And then when it's 0, it's not gonna go over this stuff. So if player counts different than 0, and this is player spread, not player counts. Then I run this stuff. Then I make here player counts. Actually, let me think. I need to do it like, I need to check here because I should do this calculation here because then I'm checking here to see. So here I just reduce based on the spread. Or maybe increase actually. No. Let's see. So it's 4 to... And that's the problem. I want to skip the positions when there's a player spread. But if I increase the player count, then it's gonna give me the wrong positions. Let me think. Player count. Let's say it's 4 here. And spread is true. So minus is not the correct. There's 4. The first one should go to 3 instead of starting on 1. Oh, the other problem is that I'm increasing player count here. So it's gonna be 2 instead. So I guess I need to use the player map. Yeah, it's probably better to use the player map because it's easier. Unless I start with 0, that also works, I guess. And do the same way. So the idea that I have is to decrease each time it goes through this until it gets to 0. Oh, but that's another problem, because then it's gonna mess up the player spread each time, because I'm changing the player count. Hmm. So if there was no spread, then I think it would work just by decreasing each time. So the first time he hits this, the player is gonna be the early position, because it's round 1 and starts with the early position. And then it would go all the way until it gets to 6. But then player count would be 0. So I think it would be 1 still, because when you get to 6, I would decrease after. And then it would work. But with this thread, the player count just starts at the... So I guess it works if I just add, and then if I use another thing there. If I use player map, maybe. So maybe if I do it the same way that I was doing before. Let me go back and think about it from the other way that it was before. It's really confusing. So I think it was like this. And so I'm increasing the position based on the spread. So I think this is good, actually. But the difference here is that I can't do it like this, because that's the problem. It's not based on the value can't be based on the order that they have been placed on these lines, because it doesn't look like it is correct. It has to be based on the order of the actions after the round 1. That's the issue. So I think I do it like this, but then I just increase the ID based on whether or not there is a spread. Oh, I need another variable to know how many times this has been here. Because it needs to be based on how many times. I think this part I can leave it like this. I'm just gonna remove this. And then I'm gonna increase the number based on the spread. So I need to create another flag variable, I think. And then based on this flag variable, I decrease the flag variable each time after the loop, after it goes through this. And I think I can remove this thing. Place it like this. So what is the name of the variable that I'm going to create? But the issue is that, I don't know, it feels wrong to do it like this. It's like there's something about it, I think. That's why I'm trying to avoid it. And what I can do is make that variable equal to player count here. And then I decrease the variable each time to keep track of the amount of times that's the thing has been through here, so I know how to change the number or how to place it. I guess instead of increasing, I can just initialize. No, I don't think. I have to increase to know how many players there are on each hand. I can't think about any other way to put it if I don't create another variable. Because how I'm gonna know when is the first time that it's getting through here, so I can, instead of using the map, can I use the problem with the actual numbers is the whole thing that is gonna change all the time. So I can't really rely on that, I think. And if I decrease the player count each time, then this thing changes. The player's front changes. And it doesn't make sense to use the map because it doesn't matter. It doesn't matter if I initialize there in the beginning of the hand. To keep track, doesn't matter. And so I think the only way is to create another variable. Maybe I should start with 1 as well. Player position. And then delete this thing here. Oh, actually, it makes more sense if I make it equal to player count. That's the whole thing about the reference thing. That's because there isn't a pointer. I'm not sure. Because I'm not sure. I don't remember if it's gonna change the initial value. I think it is not. It creates a different namespace for player position. If I do like this. Because it's creating a copy, not a reference. But I don't remember it all. New position. I think it's better if I just put it as 1 and then increase each time. Also thinking about whether or not to choose 1 or 0. Because I think 1 makes more sense. Player position, because it is going to be the same as the player count. The only difference is that I'm going to decrease this each time. So I know like the order of things here. Yeah, but that's the thing, because then it's gonna be an issue because it's gonna increase too much. Oh, or maybe I can do 0 here. Yeah, that solves the thing. Oh, but no, it's not gonna solve it because then it's gonna rewrite here. I think I'm gonna stop here. I'm gonna think about this off stream. But what I wanna do is get the position based on the order of actions after the round 1. And the challenge is figure out how to do it based on the spread here, because there might be situations where there are less than 6 players, like here, and then it would be different, because you can also have more actions than 6 players as well on preflop. So you can't make, like, the condition has to be to only get the positions up to the amount of players that exists. And then after I figure this out, then I still have to think about how to translate the sequence of actions in just maybe some tree or something that allows me to get the bets for all the players in a way that makes sense to put it here on this simulation. So I'm gonna think about this off stream, because I'm gonna take a break and then I'm gonna have to spend some time thinking, like there's nothing you can do. So I'm probably gonna come back tomorrow, maybe actually 2 days from now. I'll come back Friday and probably continue to do this stuff here. So